First of all, I want to send you the best greetings from Niš. We are currently in our Faculty of Mechanical Engineering ceremonial room. Or as you can probably notice, this event will be recorded. So now I would like to invite Academician Professor Mahouton Norbert to chair the opening ceremony.
Thank you, Professor M.Mitrović. Distinguished guests, Your Excellencies, scientists, young researchers, ladies and gentlemen. Your Excellencies, Ambassador of the Commonwealth of Australia in Serbia, Mrs. Ruth Stewart. Ambassador of Canada in Serbia, Mr. Gilles Norman. The Academician Vladimir Milovanovic, member of the Serbian Academy of Sciences and Arts. The Dean of the Faculty of Mechanical Engineering, University of Niš, Serbia, Professor Nenad Pavlović. The head of the Center of Applied Mathematics of the Faculty of Mechanical Engineering, University of Niš, Professor Melanija M.Mitrović. Okay. The members of the International Organizing Committee, my colleagues, Professor Pilippa Pattison, University of Sydney, and Professor Dragana Martinovic, University of Windsor, Canada. The members of the program committee, the members of the local organizing committee, all other protocols observed. I'm fully honored to be part of this distinguished gathering of top-level scientists and eminent persons, and to have the pleasure to address them some welcome remarks on behalf of the International Organizing and Program Committee members. First of all, allow me to express my gratitude to the individuals who have worked tirelessly towards the preparation of this great conference held to foster excellence in science through knowledge sharing in mathematics and social sciences. Your efforts put the conference series, Algebra Without Borders, on the global stage of advancing utilization of algebraic structures in all life sectors. Indeed, the 2021 edition of this series develops such an important topic as mathematics for social sciences and arts, algebraic modeling, focusing on the bridge role of semigroups and in social science mathematization. It gathers an international team of speakers with expertise in different disciplines to help shed light at ways in which mathematics is learned, understood, communicated, applied in various domains, and in dialogue with other sciences. In addition to the discussion about complexity, interdisciplinarity, leadership, mathematical cognition, semiotics, linguistics, education, this year's conference will treat algebraic thinking, modeling in social sciences and arts, and the state of the art and perspectives in semigroup theory. Looking at this rich program split in 3 days, we're sure we will have fruitful discussions and enjoy our conference. You then well understand why I want to express our gratitude to all people who are supporting us in this new adventure that gives a response to the requirements of interdisciplinarity and necessary dialogue and marriage of all life and social sciences to face contemporary global challenges. I therefore, on behalf of the program committee members, would like to thank Your Excellencies, the Ambassador of the Commonwealth of Australia in Serbia, and the Ambassador of Canada in Serbia, the Faculty of Mechanical Engineering of the University of Niš, and other anonymous persons for their accompaniment and support to this conference towards their effective presence at the open session. Finally, allow me to reiterate first and foremost the value of having this first edition in Niš, even virtually. A so beautiful city, a historical city full of emotions, majesty, and grandeur, engaged of a successful conference. We are very happy to be here, at least virtually, being unable to attend physically this scientific meeting and to live and appreciate the cultural now and historical wealth of your great country. This is only a postponement. Thank you for your kind attention. Distinguished guests, Your Excellencies, scientists, ladies and gentlemen, I'd like to invite the Dean of our host institution, the Faculty of Mechanical Engineering, University of Niš, Serbia, Professor Nenad Pavlović, to address his greetings to the participants of this conference. Please, Professor.
Ladies and gentlemen, dear colleagues, on behalf of all the staff at the Faculty of Mechanical Engineering in Niš, I have the great honor and pleasure to greet you. Let me introduce our faculty in the next few minutes. In 1960, our faculty was founded as the Department of Mechanical Engineering of the Faculty of Engineering in Niš. Since 1971, Faculty of Mechanical Engineering in Niš began working as an independent faculty. Our faculty is one of the 14 faculties building University of Niš. Something about our employee structure. At the moment, there are 96 professors and teaching assistants. There are also 5 expert associates employed as young researchers working on national projects, 45 non-teaching workers, as well numerous teachers and associates from other faculties and from the industry. Something about our study programs. The main studying program is mechanical engineering on all 3 levels of studies: graduate academic studies, 4 years in duration, master academic studies, 1 year in duration, and PhD studies, 3 years in duration. After the second year of studying, each student of mechanical engineering can choose one of 5 existing modules or specializations. These are energetics and process technology, production and information technologies, traffic engineering, transport and logistics, mechanical construction, development and engineering, and finally mechatronics and control. These modules are at the same time separate studying programs at the level of the master academic studies at our faculty. Since 2012, we have been realized studying program engineering management, graduate academic studies, 4 years in duration, as well as master academic studies, 1 year in duration. There are 5 existing modules at the level of the master academic studies of the studying program engineering management. Something about the number of students, number of enrolled students in this academic year, about 240 students at the level of the graduate academic studies, about 222 at the level of the master academic studies, and the 8 new enrolled students at the level of the PhD studies. Total number of students in this academic year is more than 1,500 students. Among them, about 1,050 students at the level of the graduate academic studies, about 400 at the level of master academic studies, and about 60 at the level of PhD studies. In this year, we have been performed several international research and scientific projects, among them 3 projects within the program Horizon 2020, 2 projects within the program Erasmus+, 1 bilateral project, and 5 projects within the CEPUS network. Beside this conference, we will organize 2 scientific conferences in this year, the 8th International Conference Transport and Logistics, as well as International Conference Classical and Constructive Semi-Groups and Applications. Ladies and gentlemen, dear colleagues, the Faculty of Mechanical Engineering will always be a representative place where the experts and the scientists from the field of applied mathematics, especially in the field of engineering, gather together. As the Dean of the Faculty of Mechanical Engineering in Niš, I'm honored to greet all the participants of the conference and wish them a successful event. Special thanks to Her Excellency, Mrs. Ruth Stewart, the Ambassador of the Commonwealth of Australia in Serbia, as well as to His Excellency, Mr. Gilles Norman, the Ambassador of Canada in Serbia, for the patronage of the conference. Faculty Information System will work hard in the next 3 days to give us technical support and to enable the smooth running of the conference. Thank you for your attention.
You're welcome, Professor Nenad Pavlovich. It is now my honor to invite the Ambassador of the Commonwealth of Australia in Serbia, Her Excellency Mrs. Ruth Stewart, to address some words.
Thank you very much, Professor M.N.Hounkonnou. I just want to make sure everyone can hear me. Yep, great. Thank you very much. Firstly, good morning, everybody, or good afternoon, or good evening if you're in Sydney or elsewhere in Australia. And I'd like to say I'm very, very happy to be here today and to be addressing such an important conference, really looking at a very exciting field of the connection between mathematics and the arts and humanities. And I'm a little bit off script with my speech, but as a former humanities student who loved the humanities and has a very analytical brain, I think this is a perfect kind of connection. And I wish that I'd had more work done in this field when I was studying to help me really bring the two together. I'd also like to thank the faculty for pulling together this conference, and particularly Professor M.N.Hounkonnou. I know it's a lot of work to organise a conference like this, so I very much appreciate all of your efforts. Thank you also, Dean Petrovic, for your introduction to the faculty. That's very useful for us as well, so we very much appreciate that. And thank you to everybody from all around the world for participating. One final person to thank, I'd like to thank a former student of the University of Niš, Mr. Jovan Milic, who connected us to Professor Mitrović and has been a long time contact of the Australian Embassy in Belgrade and really helped to bring us more connected to Niš. So thank you also to Jovan. Finally, thank you to Professor Pilippa Pattison, Deputy Vice Chancellor from the University of Sydney in the education faculty. I always really love seeing Australian connections with Serbia and my other 2 countries of accreditation, North Macedonia and Montenegro. There's so much that we can connect on and talk about. And of course, University of Sydney has a very great and prominent archaeological project here in Serbia, the GLATS project, which is doing some fantastic work in excavating Roman ruins here. So it's great to see another area of cooperation with the University of Sydney. So I know that today's conference is going to explore some really important interdisciplinary areas. So research in how mathematical and statistical analysis is being applied to understanding human behaviour, the human mind, how it works, how we interact with each other. And so in preparing for today's conference, did a little bit of thinking about, what does that mean for us in today's world? And the obvious thing that we all think about today is the COVID-19 pandemic and how that's impacted us. And if you look at research in that area, there's a lot of scientific research, hard science, I guess you'd say, into things like vaccines, but there's also much more humanities type research. Why do diseases spread the way they do? through human populations. You know, what about the impact of social networks, which I know is something that Professor Pattison has done quite a bit of work on. You know, how do we use this humanities research, mathematics, modelling, to bring a really interdisciplinary approach to our learning about the world, and how can we apply that to achieve better results for all of us as human beings. So I think it's a great topic for the conference. It's something new and different for me to learn about. And as someone who's not a scientist, I do appreciate the structure and the rigor that mathematics brings. And I think for a lot of us ex-humanities students and always lovers of the humanities, we really love seeing that analysis and rigor coming into the work that we do in our lives, and we know that it's very important to have that interdisciplinary approach. One of the things that we've done a lot of here in the embassy over many years, and in my role in other embassies around the world, in Southeast Asia, for example, is talk a lot about STEM, science, technology, engineering and mathematics, and its role, this really critical role in being part of the way in which we develop solutions to global problems. And we do a lot of work also on gender equality. How do we get more girls involved in STEM? How do we make sure that as our world changes, everybody is able to come along on the journey? And I think that one of the challenges with that approach is that perhaps we're a little bit out of date, and there's so much talk now, not about STEM, but about STEAM, and the importance of including the arts in this conversation, and understanding that, you know, if you only focus on that technical side of things, for some people it can be a bit of a barrier. It can be a little bit daunting maybe, and the creative aspect of STEAM, the arts, how you bring in different ways of thinking and problem solving, really does allow us to expose students at a much younger age to the STEM world in a way that maybe is a bit less intimidating, but also helps us think about different results and solutions to problems. And so it's not exactly the topic of this conference, but it's very connected, because really what we're talking about over the next few days is the importance of connecting disciplines. And that is really, really a crucial thing. So when we talk about STEM, and diplomats do it a lot, I think we probably need to update what we're talking about and talk a lot more about STEAM and about how we bring the arts into the conversation. And I think that the results for women's participation would improve in that context, because sometimes I think the hard technological thing can be a bit intimidating, and so this is a really important development, and making mathematics accessible and easy to understand for arts and humanities students is the other side of that equation. And I really think that that's where you're going to do some really great work during this conference. So I wish we'd talked about STEAM more and STEM a bit less, but I also think that all of you can help us to understand that more. I really hope that you get a lot out of the next few days. Ensure that humanities are part of the science conversation, but also ensure that mathematics are part of the humanities conversation, because we get a better outcome for all of us when we have a cross-disciplinary approach. So once again, I'd like to thank the organisers and everyone for being here, and I wish you the best of success in coming days, and I look forward to the conference. So thank you very much.
Thank you, Mrs. Rod Stewart, for your support to our initiative. I would like now to invite the Ambassador of Canada in Serbia, His Excellencies, Mr. Gilles Norman, to address some words to our participants. Please.
Thank you, Professor Hounkonnou, organizers, participants, ladies and gentlemen. Thank you for your invitation. It's an honor to join you today. So I'm Giles Norman. I'm the Ambassador of Canada to Serbia, North Macedonia, and Montenegro, like my colleague Ruth. And the conference program today is very substantive. It's a testament to your hard work of all the organizers, from the Faculty of Mechanical Engineering at Niš, University of Abomey-Calavi in Benin, and University of Sydney, obviously in Australia, and Windsor in Canada. So to all the organizers, I congratulate you on your success in bringing this all together. Well done. For promoting dialogue across continents, and for the contribution you're going to be making to the advancement of algebraic modeling. So a famous comedian used to tell a joke. He said, "I was thrown out of college for cheating on a metaphysics exam. I looked into the soul of the boy next to me." I must say, I feel I'm a little bit exposed here, speaking to a group of serious mathematicians such as yourselves. People who are accustomed to modeling complex phenomena in abstract terms. As an ambassador, I'm accustomed to delivering messages often aimed at leaders in government and civil society and business. And these messages are intended to share information and to communicate principles and promote certain actions, sometimes to discourage some types of behavior. But you're quite a different audience from the groups that I'm used to talking to. So I'm really wondering how you're going to access my remarks. I fear you may conclude the theoretic Shannon information content of my speech is precisely 0. I hope, however, despite your reputation for analysis and precision, that you will not be too difficult audience for me. So today I'm just going to make 3 quick points on 3 closely related topics: diversity, innovation, and the importance of your work. So turning to diversity, the conference has been organized by a team spanning 4 continents. The agenda brings together participants from around the world and from a range of cultures and disciplines. And I think you understand the importance of diversity just as much as anybody else does. We become more informed, more efficient, and more productive, not when we surround ourselves with people who are exactly like us in an echo chamber. We become smarter by working with people who have different perspectives and different approaches, and we learn from them. As a diplomat, I spend a lot of time encouraging collaboration in international relations, and I strongly believe that diversity is a source of strength. So I congratulate you on the genuine international breadth of this conference. I also encourage you to share the benefits of your research with people outside your field. So look for ways by which society may gain from the knowledge you have acquired and obviously possess. In terms of innovation, I work for the Government of Canada, and as a public servant, I'm encouraged to be innovative. Within our government, there are efforts underway to empower public service servants with the tools to undertake data analysis. There's a drive to make data more relevant to policymaking. The idea being public policy will better serve citizens and achieve better outcomes if it is based on a sound understanding of the challenges faced by different segments of the population and on real data. So the modeling work that you do has an impact on the work done by people like me, public servants. And therefore, I am definitely grateful for your work, especially as you apply it to real world problems. So finally, that's a good segue to the importance of your work. The University of Nice has played a key role in organizing this conference. I want to thank you again. The University of Nice already has a really good reputation for us here at the mission team in the Embassy of Canada. You are our partner in promoting the values of Canadian society and literature through our Canadian Studies program. So again, thank you. Some of you may know Nice was the birthplace of the Emperor Constantine. In the time of Constantine, an important tool of analysis was astrology. And according to legend, when Constantine founded Constantinople, he asked the astrologer Thales to predict the city's future. I think our tools of analysis have advanced since then. But despite the incredible advances we have made, our perspectives can still be limited by a reflexive desire to look for easy answers, to take shortcuts to genuine intellectual effort. Your work follows a more rigorous methodology, and that is to be credited. I hope that you will be successful at this conference in contributing to the advancements of genuine understanding of the world around us and a more profound understanding. So thank you once again for the opportunity to join you today. I wish you great success in your discussions and good luck. Thank you.
Thank you, His Excellency Mr. Gilles Normand, for your support to our initiative. So I would like now to invite my colleague, Professor Mechnical, to share the next session.
Okay, thank you, Professor Hounkonnou. But as you are our first speaker, it is my great pleasure to announce your talk titled Problematic of Mathematics and Social Sciences and Ubiquitous Constructive Interaction in Algebraic Modeling.
Okay, thank you, Professor Mechnical. My talk is about problematic of mathematics and social sciences and ubiquitous constructive interaction in algebraic modeling. It's a joint work with Professor M.Mitrović. So I will first speak about motivations, the role of mathematics in society, and then the relation between mathematics and social sciences, then about algebraic modeling in social sciences, and semi-group as playing a bridge role. Then mathematics and social science in the epoch of global sciences, the new challenges we face too, and then I will end with some conclusion remarks. In the preface to the abstract booklet of this conference, mathematics is defined as a subject that plays a key role in our modern civilization as a tool to understand and function in society, and as bearer of a tradition with roots in many of the world's ancient cultures. So mathematics is used to research the universe, systematize experiences, and describe and understand natural and social relations. Even nature also embraces mathematics completely. Observe any natural thing and find out symmetry or pattern in it. Change of day into night, summer into winter, etc. In plants, there are innumerable examples of symmetry, shapes, patterns, etc. To paraphrase Sunita Hadev in 2019, mathematics reveals hidden patterns that help us to understand the world around us. It plays a predominant role in our everyday life, impacts the development of social, intellectual, vocational, moral, cultural, and spiritual abilities, but also feeds education system, economics, the advancements of science and technology, the agriculture, etc. Mathematics can be seen as a soil in which other sciences, technologies, and applications are deeply rooted. If you want good fruit and harvest, the soil must be covered. The future science will need new soil to grow. They will need new mathematics. And as well summarized by Sunita Hadev, mathematics occupies a crucial and unique role in the human societies and represent a strategic key in the development of the whole mankind. All these manifestations of mathematics in our life incite to ask the following questions. Why do mathematize social science? What are the story and dynamics of their core routine? Do their interactions induce new development and benefit to these fields? Are semi-groups relevant in social science algebraic modeling? What about contemporary challenges in this epoch of global science? Following Darcy, the social sciences are usually divided into the fields of anthropology, economics, geography, political science, psychology, and sociology. Demography is also included, but is typically treated as a subdivision of sociology. Linguistics may be included, but history seldom is. And a historically important reason for the mathematization of the social science was that mathematics is associated with precision and objectivity. These are two requirements and any science should satisfy. And so the mathematization of the social sciences was considered to be a crucial step that had to be taken to turn the social sciences into real science. It is a mistake, however, to overestimate the role of the mathematics. At the end, mathematics provides the social scientists only with tools, and what one obtains when using these tools will crucially depend on the assumptions that are made. This is a variant of the well-known GIGO principle from computer science, garbage in, garbage out. All assumptions are motivated informally. Formulating them in the language of mathematics just helps putting them more precisely. And once the assumptions are formulated mathematically, the machinery of mathematics helps to draw inference in an automated way. There are also several other reasons for the mathematization in the social sciences like theory representation, theory exploration, theory testing, heuristics, explanation, understanding, etc. So now, what is the story and the dynamics of all these movements? Globally, following Paula and Martin, scientific theories usually do not directly describe the natural phenomena under investigation, but rather a mathematical idealization of them that abstract any away from various complicating factors. For instance, the mathematical idealization used in formulation in linguistic theories are often called representations or models of the phenomena in question. The techniques drawn from areas of mathematics, such as set theory, logic, algebra, and formal language theory, are usually described as discrete, as opposed to continuous, such as calculus, differential equation, Fourier analysis, or probability. Sets are basics of mathematical entities that are useful for structuring linguistic and any other science representation. Sets theory is the workspace where the idealized representation of natural phenomena by linguists and other scientists is carried out. Applications of mathematics in other sciences often take the form of a network of relations between certain objects belonging to a set. Even more, relations play a basic role in system theory. The mathematical treatment of relation is said to have its origin in Aristotle, but its model starts with the contribution of George Boole, Augustus de Morgan, and Charles Peirce. Intuitively, following further Paula and Martin in 2015, a relation is a sort of thing that either does and does not hold between certain things. For example, the love relations hold between Kim and Sandy, just in case Kim loves Sandy, and the less than relation holds between two natural numbers, A and B, just in case A less than B. Many different kinds of logic can be directly applied to formalizing theories in social sciences. For example, linear logic, Lambert calculus, intuitionistic propositional logic, typed lambda calculus, dependent type theories, and higher order logic. As set by Hartmann and Springer, social scientists use a wide variety of mathematical methods, and methods imported from the formal and natural science in the social sciences include algebra, calculus, the axiomatic method, logic and set theory, probability theory, linear programming, topology, graph theory, complexity theory, statistical, mechanical methods, considering the society as many body systems, like a gas is a many body system composed of molecules. Besides providing various methods that can be used to study social phenomena, the natural sciences also inspired a certain way of addressing a problem. In recent years, for example, various methods from computer science have been incorporated into social science research as well. There is also a strong trend within computer science to address problems from the social sciences. An example is the recent establishment of the new interdisciplinary field, computational social science, which is dominated by computer scientists. Interesting enough to do much work in computational social choice uses analytical and logical methods. There is, however, a strong trend in the social sciences to use powerful numerical and simulation methods to explore complex dynamical social phenomena due to the availability of high-powered computers. New developments in mathematics, in science, including social sciences and technology, inspire new mathematical insights, new mathematical theories, and new application of already existing mathematical theories. Mathematical methods that emerged from problems in the social sciences include powerful instruments such as decision theory, utility theory, game theory, measurement theory, social choice theory, and judgment aggregation. and the later theories were invented by social scientists for social scientists and with a specific social science application in mind. What is their core routine? They help addressing specific problems that arise in the context of the social sciences that did not have an analog in the natural sciences when they were invented. Interestingly, there are also methods that cannot be attached to one specific science, like the network theory studied in almost all sciences, inducing parallel developments within them. To the questions, which method is appropriate for a certain problem, one can only answer on a case-by-case basis, and it is part of the ingenuity of the scientists to pick the best method. Mathematics and related discipline provide the scientists with a toolbox out of which they have to pick a tool, the best one adapted to their specific problem. It is common to say regarding algebraic modeling in social science that the core activity in social science is model building. To a phenomenon occurring in any field of studies, including social ones, can correspond different mathematical or algebraic models from already existing or their own systems ones. Algebraic ones are one of the central topics of this conference. Following Hechten, the algebra is not only a subject with an independent life and vigor, it is one of the important current research areas in mathematics. It also serves as the unifying thread which interlaces almost all of mathematics, geometry, number theory, analysis, topology, and even applied mathematics. Algebra is beautiful, said Lead and Pierce. It is so beautiful that many people forget that it can be very useful as well. To paraphrase Worsley, can the whole of modern algebra be described in a couple of sentences? Yes, it can. It has been designed to be elegantly simple. The story starts with sets, collection of objects, and relation of them, and proceeds to the concept of a semigroup. Each new concept is based on the previous one, and ultimately, the whole multi-story edifice rests on the sparse foundation of set and relation. Semigroups serve as the building blocks for the structures comprising the subject which is today called modern algebra. A semigroup is an algebraic structure consisting of a set with an associative binary operation defined on it. Jean-Paul Boyd wrote in his book, semigroups have such a simple definition that it is sometimes hard to believe that anything can be proven about them. A semigroup is the simplest possible mathematical object since it has only one set, one operation, one axiom, and many common examples. And sets of relations closed under composition are examples of semigroups, giving rise to interesting non-trivial ideas, providing links both in result and methodology with other mathematical disciplines, as well as other sciences. The capability and flexibility of semigroup from the point of view of modeling and problem solving is extremely diverse situation have been already pointed out, and interesting new algebraic ideas arise with binary application and connection to other areas of mathematics and sciences. To say that applications are important in algebra is a platitude. History shows that good algebraic theories never originate axiomatically. The way they are taught in many textbooks, they rather spring out of application. They are discovered. One can invent a set of identities and similar axioms and spend years looking for clever properties of algebra or classes of algebras defined by these axioms. This is not the way good algebra is done. From that point of view, the link between semigroups and social sciences is an important interface between Thank you. The link between semi-group and social science is an important interface between semi-groups and the outside world. They both mention chain review of Jean-Paul Boyle's book. It is also written, semi-groups do appear very naturally in various studies known under the common umbrella name of social sciences. Yet, to see them, one needs eyes. One of the important purposes of this event is to bring together experts from social sciences and semi-group theory to stimulate discussion of recent results in those domains. And semi-group theoreticians, participants of this event, to have eyes. Now, what about new challenges? Complexity as a phenomenon related to various areas of life is increasing, and mathematics to model and tackle its challenges needs to develop side by side. What is happening? This is a question where collaboration between various fields of mathematics with life sciences, social sciences, modern technologies, and computer science will be required, according to the European Union Commission report in 2016. Mathematics is recognized today as essential and indispensable for addressing the major challenges in sciences, technology, and society. New and sophisticated mathematical tools are required to process the abundance of data on social, technical, economic, ecological, and technological systems and help tackle pressing societal challenges while enabling the necessary technological advances. Current developments in big data analysis and high-performance computing mathematical bases have shown that existing areas of mathematics formerly deemed merely theoretical, such as algebra and topology, are now very important for these fields. It is therefore impossible to predict what mathematical areas should be in the focus now to be exploited in 50 years. Quite importantly, we should emphasize the need for collaboration and increasing convergence between different mathematical disciplines as well as between mathematics and other sciences. The future of mathematics lies in collaboration with state-of-art sciences. New convergent fields of science and mathematics are being conceived. Equally important, many areas within mathematics are converging and increasingly interaction. Indeed, substantial interaction amongst mathematicians and with other scientific disciplines is required to meet the needs of data-driven science and modern innovation. In today's mathematics, it would be artificial and counterproductive to draw a boundary between theory and application. It is preferable to ensure a continuum between theoretical and applied mathematics and overcome the shared approach of traditional mathematics. To these aims, mathematicians need training, incitation and incentives, and the creation of interdisciplinary and inter-mathematical teams to stimulate new ways of collaborating. On the other hand, equally important, mathematics should not only focus on nowadays application, but should leave room for development, even theoretical, that may be vital tomorrow. Social sciences are an important field where mathematics should be implemented as also imposed by the development of complex systems or modeling and data analysis. To sum up in a nutshell, let's paraphrase Roger Bacon, an English Franciscan friar, philosopher, scientist, and scholar of the 13th century. Neglect mathematics works injury to all knowledge, since he who is ignorant of it cannot know the other sciences or the things of the world. Contemporary mathematics rely on the collaboration between different mathematical fields. Mathematicians must collaborate across mathematical fields as well as across the borders between sciences. They must build bridge with physics, biology, chemistry, and increasingly also social sciences and humanities. Mathematics and social sciences must be deployed in technologies and nature-based solutions to strengthen and support research and innovation in multi, trans, and interdisciplinary way in a real solid partnership to address the outstanding challenges. Science is a global endeavor, and the last year, more than any other, has demonstrated the power of global science. Thank you for your kind attention.
Thank you, Professor Hounkonnou, for your talk. Next session. It is my great pleasure to invite one of our organizers, Professor Pilippa Pattison, to give her lecture titled Algebraic Approaches to the Analysis of Social Networks. We can reach Pip till we solve the problem. We can go on. I can see that Misha Volkov is here with us. Misha, can you go on? Can we go on with your talk?
Yes, if it is necessary, I can, of course. But
yes, it is our great pleasure to have you with us today. So, Mikhail Volkov and his talk, Simmering Identities of the Branch Monoids.
Okay. Can you see my screen?
Yes, yes, you can go on.
Okay, so hello to everyone, and thank you for the invitation. I realize that this conference is very mixed, and the audience is probably not, how to say, evenly prepared. So my talk, therefore, will be very, very elementary, actually. Still, I hope it will be of some interest for semi-groupists, because maybe some of the facts which I will report will be new even for specialists. But the requirements that are necessary to understand these talks are minimal. Probably you don't even need to know the definition of a semigroup to understand this talk. So I'm going to speak about identities or laws. The concept of an identity is a very basic concept, and arguably it is one of the very first abstract ideas that children encounter when they start to study mathematics at school. What I mean by a law is something like the commutative law of addition. So A plus B is equal to B plus A. So a sum is not changed at rearrangement of its addends. And I think it is one of the very first mathematical facts which children learn. And at the end of the high school, a student should know, and at least we suppose that he or she knows, a good dozen of laws, say commutativity and associativity of addition, commutativity and associativity of multiplication, and so on and so on. What is important for this talk, I think a student may feel, probably the student cannot explain this feeling, but I think they understand the idea that some laws are more important than the other ones. That there is a sort of grading between these mathematical facts. Some are more fundamental in a sense. For instance, I mean, they are taught that they are laws. We bracket them on the blackboards and screens. We somehow emphasize the importance. That's why the student understands that these laws somehow stand out. For instance, these laws like commutativity of multiplication or associativity of multiplication are these main or primary identities. And for instance, this law, it is also a law, it also holds if you multiply numbers or polynomials. So if you multiply AB with itself, so it is the same as A squared, B squared. It is also law, but somehow it seems to be less important. Why? Because we can explain the difference. I mean, we don't do it when we are teaching elementary mathematics, but now we can explain what is the real difference. Such primary laws like commutativity or associativity are in fact properties of objects, say numbers we multiply, and the way the multiplication is defined. While these secondary laws can be formally inferred from primary ones. And for this inference, it is not important which objects are multiplied and how the multiplication was defined. This is an elementary example of such a formal inference. So suppose we start with AB squared, it's AB by the very definition of squaring. Now, the associative law allows us to redistribute parentheses, so to regroup this in this way. Now we can use the commutativity to change the order of factors here. And now we again use associativity to regroup factors again. And now we again use the definition of squaring. And we deduce formally, we formally infer this law from associativity and commutativity. So this identity example is a formal corollary of associativity and commutativity. And this means that this law holds whenever and wherever the two laws, associativity and commutativity, hold. And for instance, in the elementary mathematics in high school, we gradually extend the numbers we deal with. We start with natural numbers, positive integers, then we come to integers, then we come to rationals, then to reals, and sometimes even to the set of complex numbers. And every time we basically have to reprove these laws, commutativity and associativity, because we change the definition of multiplication and we change objects that are multiplied. But as soon as we proved this basic law, there is no need to prove again anew this consequence, because it is a formal corollary. It holds wherever the two basic laws are valid. And actually, a big part of algebra deals with inferring some useful secondary identities from some primary laws. If you analyze what is going on in, say, university course of linear algebra, you see that basically you are proving some identities. For instance, look at this identity, the product rule for determinant. So the determinant of the product AB of two square matrices is the product of the determinants. If you write it, this identity in the expanded form, using the definition or explicit formula for determinant, it is an awful identity. It's very complicated. Yes, it is due to good notation. We can write it in a compact way. So it is incredibly complicated identity, non-trivial, but in fact, it is a consequence of very few basic identities, basically of common rules of multiplication and addition, and their But the inference is, of course, non-trivial, but the number of these primary laws which are used in the course of the inference is not big. And this observation leads to the idea of composing a complete list of such primary laws that would allow us to infer every possible identity. Yes. And such a list is called an identity basis. So we define what is an identity basis. The word basis is a bit misleading. It is traditional, but we don't mean any independence. So it is not like a basis in a vector space. It need not be unique. It is just some sort of generating system. So just we have enough identities that allow us to deduce everything we need formally. Of course, in order to speak about an identity basis, one has to specify which identities are considered. More precisely, one has to specify a set of objects, say numbers or functions or matrices or polynomials, and a set of operations on these objects, say addition or multiplication or exponentiation. And let me explain these ideas on an easy example, which everyone knows. Let our objects be natural numbers, so positive integers. And let our operations be usual addition and usual multiplication. Then it is not hard to show that the following 6 laws form a basis. So just the laws everyone learned in the basic school, commutativity, associativity for addition and for multiplication, this law which specifies the property of the identity, and this distributivity, so multiplication distributes over addition. Another high school operation on the set of positive integers is exponentiation. So we can take any 2 integers, a and b, and you can raise a to the power b. And the following 5 laws involving addition, multiplication, and exponentiation, also are very common. And we refer to these 11 standard laws, the 6 from the previous slide, these 6 ones, and the 5 from this slide as to high school identities, HSI. So arguably, Richard Dedekind, who wrote in 1988 sort of booklet, was sind und was sollen die Zahlen? What are numbers and what are they and what they should be? Who basically asked in some maybe not so explicit form if these 11 basic laws are sufficient to tell us everything we could want to know about the natural numbers. However, at this time, no mathematical language existed in which such a question could be stated precisely. Such a language was developed much later in the first half of the 20th century, and Alfred Tarski was one of the major contributors to this development. And in the 60s, he explicitly formulated the problem in the terms that we used nowadays. It is called Tarski's high school identity problem. Do these laws, do these 11 laws, form a basis for the identities that involve addition, multiplication, and exponentiation, and hold in N, in the set of positive integers? Surprisingly, the answer is no. These identities are not sufficient to develop everything which holds true for these 3 operations in the set of natural numbers. So it was Alex Wilkie, a mathematician from Oxford, a logician actually from Oxford, who found the following identity that holds on positive integers, but cannot be deduced from the 11 high school identities. This is this identity. It involves two letters, A and B, and number 1. It looks relatively ugly, but in fact it is easy to show that it holds now. That indeed, if you take any two numbers, A in B, the left-hand side part and the right-hand side part will be the same. A more delicate question is how to prove that this identity cannot be inferred from H as I. It is a non-trivial mathematical task, but it can be shown. One can use what is called a counter model. Define an abstract set M with 3 operations such that all these identities hold in M, but Wilke's identity doesn't hold. Well, it's an unpleasant surprise, of course, and yes, the counter model can be finite. Has only 12 elements. The current record has only 12 elements. And the question is, can we save the situation by including these Wilke's identities in the high school curriculum? Fortunately for kids, it is not possible. I mean, it would be a disaster if in the high school they had to study or to learn also these identities, but it makes no sense because the identities of this structure, natural numbers with plus, multiplication and exponentiation admit no finite basis at all. This was shown by Gurevich in 1990. Actually, the paper was published in 1990. It was submitted in 1984. It was long under review. And it was published after the author's untimely death, unfortunately. And what does it really mean? It means that if one chooses any finite set sigma of identities that hold here, there always exist an identity that plays the same role with respect to sigma as Wilke's identities does with respect to these 11 basic rules. It is true, but it cannot be inferred. And therefore, it makes no sense to make such a list for our school children because at least cannot be found. Okay, and here we encounter the situation when we have a very natural and very simple structure, but its identities are complicated and admit no finite basis. In this situation, we say that the answer to the finite basis problem for the structure is negative and the structure is non-finitely based. So otherwise we say that the structure is finitely based. So this structure, natural numbers with addition and multiplication, is finitely based, while this structure, natural numbers with 3 operations, is not. And what the result which I will mention at the end of this talk is related to this finite basis problem, but not for natural numbers, but for another object which is natural too. And the general finite basis problem can be formulated in this way. We are given an interesting structure, M, a set with a bunch of operations. And we are asking whether or not this structure is finitely based. It is quite a natural problem by itself, but also it is important because it has some very interesting connection. I'm not going to survey this, I just mentioned that on one hand, there are some results of practical importance, so we can use this solution to the finite basis problem for developing some algorithms in the formal language theory. On the other hand, some classical number theoretic conjecture, such as twin prime or Goldberg conjecture, or existence of odd perfect number, or the infinitude of even perfect numbers. All this can be expressed as a finite basis problem. This is a result by Peter Perkins, who has shown that each of these classical number theoretical conjecture is equivalent to the finite basis problem for a certain structure with one operation. Okay. What is interesting is that even a finite structure can be not infinitely based. The smallest example is a 3-element structure known as Mursky groupoid. But the most striking example is this Brandmanoid. It is a structure formed by the following 6 2x2 matrices. This is the identity matrix, that is the 0 matrix, and we have 4 matrix units. And the operation is the usual matrix multiplication. We multiply these matrices as usual, and we got a 6-element structure, which is called the Brandmanoid, and it is not finitely based. Identities that hold in this small example are infinite. This was also shown by Perkins, but in a different paper. So we see a very transparent, very natural, very finite structure whose identities cannot be axiomatized by finite means. Tarski suggested to study the finite basis problem for finite structures as a decision problem. Because the finite structure is something which can be given in a constructive way. So it can be input of an algorithm. So when presented with an efficient description of a structure, we can ask for an algorithmic solution of the question whether or not it is finitely based. This is called Tarski's finite basis problem. And is an algorithm which, when given an efficient description of a finite structure, decides whether or not this structure is finitely based. This question was answered in the negative by Ralph Mackenzie in his famous paper of 1996. And I think it is a good news. So this problem is undecidable in general. So it gives more spice, so to say, more interest in studying this for special cases, because you have to be clever on your computer to get an answer. Now, so I know that my time is already closing to finish, but I'm very close to finish too. I recall what is a semi-ring. Semi-ring is a structure with 2 operations, addition and multiplication, such that the following laws hold: commutativity, associativity for multiplication, and distributive laws. So, for instance, natural numbers give us an example of semi-ring. Observe that in general we don't request that multiplication is commutative, and that's why we need 2 distributive laws. And additively idempotent semi-ring is such that the idempotency law for the addition holds. A plus A is again A. A classic example here is the Boolean semi-ring, which is formed by 2 symbols, 0 and 1, say true and false, under the following addition, which is just the usual logical laws. Boolean matrices are matrices of this Boolean semi-ring, then can be multiplied and added via the usual matrix rules. And it is well known that Boolean matrices precisely model binary relations, which were mentioned in the first talk today, and hence they play some role in applications of algebras of social sciences. Now I recall the ground monoid. It is formed by the 6 2x2 matrices. But for this talk, it is more convenient to think of the same monoid as a set of other 6 matrices, this time Boolean. Here it was not essential where 0 and 1s came from, but now we insist that they came from the Booleans in B. The advantage of this, it is these matrices look in a different way, but they are in fact the same. I mean, they multiply in the same way. If you have this vertical correspondence, so, and you multiply matrices in the upper row and the corresponding matrices in the bottom row, you will see that the result will be also in the correspondence. But the advantage of the second representation is that now you can not only multiply but also add matrices. This set of 6 matrices is closed under the matrix addition. I recall that 1 + 1 is 1. So if I say add this and this matrix, I got this matrix. Thus, this structure is an additively idempotent semiring. And in fact, it is the only way you can make it a semiring. And my result, which is basically the main result, my talk is submitted and accepted in Algebra Universalis, and you can also look at the preprint, that this semiring admits no identity basis with finitely many variables, and so it is also not finitely based. Not only multiplicative identity of this 6-element guy are non-finitely based. The same is true for identities which involve multiplication and addition. A similar result, but for a 7-element semiring, was proved by Igor Dolenko from Novi Sad, and the same result has also been obtained recently by Marcel Jackson from Melbourne, from Australia, in collaboration with 2 colleagues, Jane and Zhao, from Xi'an in China. But the proofs in all cases are completely different. The ideas of these fellows and the idea of Dolenko is not the same. My proof is actually very simple, but I'm afraid I have no time.
We are near.
Yes, so
at the end of your time.
Yes, I finish, and thank you for your attention.
Thank you, Misha, for your talk. And now we are going again address to Pip, and we hope that we will have a more luck, and that we will be more lucky. And again, let me remind our audience that the title of your talk is Algebraic Approaches to the Analysis of Social Networks.
Thank you.
Okay. Go.
Excellent. Thank you. Excellent. So, third time lucky. So I'm going to talk about algebras in the context of social relationships broadly, and hope in that way to explain a bit of the history of the use of algebras in social networks and a range of different problems that colleagues attending this conference will be talking about. So a little bit about why social relationships are important, a general language for talking about relationships using a free word algebra, then building algebras from networks and the analyses that are of interest. And then I hope to touch on some interesting problems. The kinds of social relationships in which we're interested come in many shapes and sizes, but two key distinctions, and here in the upper left is an example that the ambassador mentioned. It's a connection amongst people relevant to disease transmission. In this case, people sharing needles in relation to hepatitis C virus transmission. And it's one set of actors and a single relationship. Moving to the right on the upper side, we've again got one set of actors. These are producers of various modes of transportation and their suppliers in the Italian transportation production industry. And here there are multiple kinds of relationships amongst the actors, supply relationships, technology transfer and equity, coded in different colours, as are their intersections for a given pair of companies. Then down on the bottom left, an example of what we call a two-mode network, where there are two sets of entities, in this case, a set of academics and a set of journals in which they publish, and connections only go between the two sets, not within the two sets. And so these types of relationships abound in the literature. And indeed, a lot of the thinking in social sciences has been intrigued for a long time by the kinds of problems that Norbert mentioned in his wonderful introductory lecture, which is about the patterns in human relationships. And from a very early time, anthropologists were intrigued at the idea that any given relationship is actually not independent of relationships amongst actors who are close to that, a pair of people who are joined by that connection. And rather, the sort of interesting social science challenge is to understand the linkages amongst the relationships in a way that helps us understand the social structure of human relationships. And Harrison White, who's been very influential in the field, talks about this very directly when he says a social tie, a connection between two people, is a relationship between actors which entails some other relationships in the immediate vicinity. So composition of relations and the idea of compound relations is fundamental to how we think about social relationships. And it's really to understand how this all works that is the core problem that we need to think about. And we need to think about social relationships as not existing in isolation, but nonetheless as a system that is, there's a lot of interdependencies amongst the relationships. So what I'll talk about mainly is two examples of this. The one mode relationship with just a single type of tie was the case of needle sharing that I mentioned. But a lot of interest in using algebras has been in the case of a single set of actors with multiple types of connections amongst them and represented as Boolean arrays often, although there is interest in connections between people that have other values, as I'll mention a little later. And there's also been great interest, and it's wonderful that Ron Brugger is joining us at this conference because he really explained the social value of thinking about a relationship between two sets as a two-mode network, and think about that relationship as holding information about the co-constitutive nature of those two sets of entities, whether it's people and the groups they belong to, or directors who sit on boards, or many other examples that have been used in the social sciences literature. So in order to talk about this, I'm going to start by talking about a very general approach to constructing algebras, and then particularize that in certain ways, but it's very valuable that some quite broad or general thinking is actually able to be applied in lots of different ways. So to talk about relationships, we're going to talk about sort of a fundamental set of relational terms or letters in a free word algebra. And they're going to be things like, being a parent of, a friend of, whatever is of interest. Close contact for COVID tracing is a contemporary example of great interest. And acting on that set of letters is a set of operations that are chosen, as Norbert said, not objectively, but through the sort of through the knowledge and assumptions that you want to make and the circumstances you want to investigate. And of course, each of these operations might take a different form. Some might be unary, like the converse operation. And of course, even in human relationships and in our own languages, there are often words that reflect the converse relationship. Mother-daughter is sort of an obvious example, but there's many others in many settings. And of the binary operations of potential interest, we've already heard about the importance of those from in the previous talk, but certainly composition is a really vital ingredient in the way in which we talk about social relationships, and our languages reflect that in many ways. So in English, mother's brother is, there's a term for that. And John Boyd, I think I saw him in the audience before. He's done a lot of work on understanding the structures of kinship relationships and kinship terms. So we think about an algebra that's made up of these things, formally defined here. I won't go through all the detail, but essentially we can build up a free word algebra by starting with the initial set of letters and applying the operations of interest to those letters to build up a language for talking about derived relationships from that initial set. And we can do that. We can actually work out, there's a that there's no constraint on how long they can be, but there might be cases where we're only interested in those that have a particular length or rank as it's defined here. And the importance of this free word algebra is that it gives us a language for discriminating amongst social relationships. And in talking about the importance of different kinds of operations or on relations, Harrison White again recommended that probably the three that we really need to think about are intersection. So when are two relationships occurring in the same place, about the converse relationship, just given the very significant nature of asymmetric relations in our world, and also composition. And so we'll look at some examples that use those three things. And of course, if we actually have some network data, which we often think as a set, for example, in the case of a multi-relational network, a set of observed relationships amongst a set of particular actors, for example, those Italian firms and the relations amongst them, that's data. And we can also, of course, think about the special relations that have been mentioned already. And we can then use the word algebra to actually create a derived relation corresponding to each word in the word algebra by applying some derivation rules to the observed data. For example, the converse is to take the transpose of the matrix, the complement is the complement of the matrix, and so on. And we then, and this was really, I think this has been recognised in lots of different contexts, it's then valuable, and I've called it here a generalised axiom of quality, that if we have some ordering, quasi-order, or we propose there's a quasi-order between the words in the word algebra if in practice, empirically, that ordering holds amongst the derived relations that we generate by applying these rules to the observed data. And that leads to then a partition on the words in the word algebra, which in this case necessarily means that we end up with a finite algebra. So we have both a partition and an induced ordering on those, on the classes of that partition. That gives us a set of equations and a set of orderings in the derived relations, in the relations that are derived from the data. And I've mentioned here that Antonio Ostwick is going to talk later in the conference and has provided some nice code to derive all of these relations. And then this gives rise to a partially ordered algebra, and so we'll define it generally in a standard way. It's a set of non-empty sets of elements. Actually, from the previous example, it's those classes of words from W, that same set of operations, and this inherited ordering, partial quasi-order. And then we assume, and it certainly applies in practice, that the operations are isotone in the sense that they're order preserving in this algebra. And of course, a family of algebras with the same set F satisfies a set of postulates or axioms. I won't go into detail here, but in different cases will lead to different axioms in the algebra. And so some cases that have been studied in the literature, it's a very nice book by Harrison White, looking at groups that arise from Australian Aboriginal marriage class systems and using permutation groups to actually understand some of the consequences or structures in those particular nations. Then a number of other applications, including a very important set of papers by John Boyd, one that looks at inverse semigroups for Omaha type kinship systems, a very nice paper in which he uses homomorphisms, as I'll mention in a moment, to actually explore the relationships between different kinship systems. And then applications to these general multi-relational networks using semigroups and partially ordered semigroups, just relying on composition. And as I mentioned, Antonio Ostwick has developed some nice software for actually computing some of these things. Another case of interest, if we take those three connections that were favoured by Harrison White, then we get a structure which is also a lattice. Non-binary relations are also of interest, and we'll hear from Vlado Batigi about semi-ring valued relations, and also from Lucia Falzon about the case where the relations are time varying. In the case of two-mode networks, and I mentioned the work of Ron Breiger earlier, and we'll hear about this from a number at the conference, including John Levy-Martin and Antonio, as I mentioned, and also Ron Breiger. In this case, the letters of the alphabet are actually the labels, or the reflect the rows of a two-mode network, or alternatively the columns. The operation set is just intersection or union, and you get a different structure in the two cases, and both have been analysed and are of interest. They either add the universal or null relation. And that's led to a lot of very interesting analysis of relational data. Turning quickly to the question of analysis of these algebras, as I said, we start with an observed network and create an algebra from it in the way described. And the interest here is really what can that analysis, what can we learn from the algebra about the interlocking of relations in the network? And can we analyze the algebra in a way that actually throws additional light on that? And then what does that tell us about the expression of those patterns in this particular network? And of course, if we've got two networks to start with, we're going to ask that in a compare and contrast way. And so in the rest of the paper, and I suspect I'm going to run out of time, I talk about situating these structures within lattices of homomorphisms in order to both analyze them and compare them. And this is something that was recognized very early when people started to apply algebras, that the ideas of homomorphisms would be very important to their analysis. And very briefly, one of the directions that I have found very fruitful is to actually think about a kind of subdirect representation, which is as efficient as it can be, and that's reflected by being a minimal irredundant subset of homomorphic images of the original structure. And that allows us to analyze a network either into multiple components or understand its a unique maximal component, and then analyze that maximal component into further components. I'm going to skip through these slides very quickly, but essentially we define here, starting with a set of algebras, their direct product, and then using and then a subdirect product, which is really just a subalgebra of the direct product, which has each of the individual constituent algebras as a homomorphic image. We then find it very helpful to use this ordering that comes along with binary relations, and actually focus not on all homomorphisms, but only those that are isotone, that is order preserving. And each of those gives rise to what I called here a pi relation. It's really the quasi-ordered equivalent of a congruence relation, and it reflects in a one-to-one fashion the isotone homomorphism. And so when we think about the analysis of the algebra, it turns out that the analysis of the lattice of pi relations is actually a very helpful way of understanding the components of the algebra. And that is the way we proceed. And so this idea of factorization that I mentioned, it comes by actually finding a set of meter-irreducible elements in the lattice of pi relations that is also irredundant. There's actually sometimes multiple ones of those, and so we then place an ordering on those, and we pick the ones that are minimal as potential factorizations of the algebra. There's a further kind of question you can ask. That is actually very helpful because you do get a recurring set of images from one network analysis situation to another, which indicates that there's some structural similarities from one network to the other. And in many cases, we can actually think that's a very helpful thing to know, and does throw some light on the structure of interlocking amongst those relationships. But we can then also ask to what degree there's a derived analysis of the network itself in terms of this decomposition of the algebra. And that leads us to the question of when a homomorphism of a network algebra is actually associated with a homomorphism of the network itself. And Nina Otto is going to give a talk on that, which I think is very exciting to see some further developments of this problem. Now, I know I've gone over time, so I'm going to skip over that, but it'll be in the slides if anyone wants to have a look. Let me finish by saying that the challenges I think that we've all experienced in using algebras in real situations with real data on social relationships is that there's often a very great deal of complexity, and we find a need to focus on the strong patterns, whether it's through some kind of pre-analysis of the network itself, or through the kind of approach that Nina Otto will talk about, an analysis that attempts to find components that are both components of the network and components of its algebra at the same time. The second challenge, and I think this reflects some of the comments from the other talk, there is, of course, a bit of an uptake barrier to using algebras in the social sciences, and the ambassador referred to this earlier. We do need to make the approaches that we've been talking about accessible to colleagues. And indeed, I think we do need to find some nice examples which actually help attract joint interest across mathematics and the social sciences. And in thinking through the sort of this quick race through the kinds of approaches people have taken, I think there's some very interesting opportunities for us. One is to actually delve much more deeply in a mathematical way into that case of converse intersection and composition for multi-relational networks. I think there's some things to be discovered there that we just haven't really understood. I do think the problem that Nina Otto will talk about is a really interesting one, a principled joint approach to identifying both algebraic and network homomorphisms. And likewise, and I haven't really mentioned this before, but my own career headed off to actually look much more closely at statistical models and using techniques that have really come out of statistical mechanics. But it would be really interesting to think about whether we can identify a principled joint algebraic and probabilistic approach to thinking about the potential models for relational interlocking. And finally, there's no substitute for engagement with rich examples, as colleagues will demonstrate in the talks to follow, so that we can learn and refine our approaches through actually using them in situations of real interest. Thank you very much.
Thank you, Pip, very much for your talks. So now we are near to begin series of contributed talks. I apologize in advance to the colleagues from this session for my possibly bad pronunciation of their names. So the first talk is titled as Algebraic Thinking and Modeling in Dance. The presenter will be Shanti Pease. Right, Shanti?
Yes, Shanti, please say. Please say. It is fine.
Okay, you can share your slides and you can start with your presentation.
Okay, thank you. Thank you so much.
Yes, yes, go on, please.
So thank you so much for giving me this opportunity to present our paper, Algebraic Thinking and Modeling in Dance. I'm Shanti Pise from Indian Institute of Science Education and Research, IISER, Pune, India. And along with me is Professor R. Ramanujam from Institute of Mathematical Sciences, Chennai, India. If you can see on the right-hand side, there is a beautiful image. This picture is of my son actually. He's taking a jump. This is called as a C jump in dance. Now, when you see or look at this picture, the first thing that comes or the thing that you imagine is it's really beautiful, it's really high, and the scenic beauty also captures. However, I want to use mathematics to understand how dance creates an enthusiasm, creates a learning. So this is what this abstract is about. Before we start with mathematical algebraic thinking, I want to go into the understanding of mathematical thinking. And according to William Thurston, he said that among all the senses, vision, spatial sense, and kinesthetic motion or sense is the most powerful for taking in information visually as well as kinesthetically. And thinking with this, we are able to see our spatial sense. So this is what is the basis of mathematical thinking, what we have considered. Now, if you ask about algebraic thinking, so what is algebraic thinking? This is very beautifully demonstrated in this cartoon. I find if you put the slash through the equal signs, the number of possible answers vastly increases. I can show you with a demonstration. I hope you can see myself, you can see my video. Yeah, so here you can see that there is a slash, right? Now, if I turn this, I can write this as x plus y is equal to 1. But what will happen when x plus y is not equal to 1? There is what the student has to think. Start thinking why it is not equal to 1. What will happen if it is not equal to 1? So this kind of thinking is what we really want to encourage in the students. And we want to include that recognizing and analyzing various patterns, studying and representing relationships, making generalizations and analyzing how things change. This is the definition of algebra that we have taken into account from CTM. Dance, by offering patterns in movement, can be enacted physically, and it creates an opportunity for all this. I can give you a head over it and just rotate, slowly start opening. It creates a pattern. Now, how create various expressions in algebra also, and this can be termed as algebraic expressions, right? So I want to employ here that dance uses symbolism, just like algebra does. And by composing these symbols, we create movement, expressions, just like we compose terms in algebra. So this is what we really want to explore. Along with this, symmetry, which is an indispensable part of algebra, is also lot of importance of symmetry is there in dance. So why not combine together? When two dancers enact the same movement, either they are doing similar things or they are doing it as a mirror image, or if you can see in this images also, or they are doing rotation. So how we can use this symmetry to understand mathematics is what we are going to do. So how we can bodily represent this 3D space and movements. So some basic steps, some basic movements we can take. And we can form some notations like, if you see here, this image, the person is standing. So it can be like I, which denotes nothing. It can be an identity. So when you move from one place to another, it is, we can denote it as T for translation. Similarly, if we rotate 90-degree clockwise, it can be termed as R. 90-degree anti-clockwise, it can be termed as L. Mirror image can be termed as M. In this way, dance in the physical form can be converted into algebraic form. And what we can do is we can try to find out the relationship. What is R, L? How can we say that R is followed by L? Can we think of L as an inverse of R? Is TR same as RT? What is RR? So like these questions we can pose to the students, and bodily representation of 3D space and movement can be done in forms of combining symmetry. So it can be made in tabular form. So if we have combinations of T and T, so what exactly we get? So we have like a 5x5 matrix we have created, and how we can fill this with the help of students. So what do you all think? Actually, this is a small question to all of you also to think about it. Our representation will help the student to understand that T and T can be happening 2T translation. L and R can actually become identity itself. L and I, because identity and left rotation is L. And similarly, we can go on finding and filling on this table. So we can understand how the student learn symmetries, and they transform this learning of physical thing into the algebraic structures. So students fill the entries by acting them out. And we can discuss questions like, describe all position in which you can switch from reflectional to rotational symmetry. Justify that you can actually use the position you found to switch between the symmetries, and explain how you can be so sure that you find all the positions. So in dance, we have rotation, we have translation, we have so many reflection pieces or choreography parts. Same we have in algebra, and how we can club this together, that is what is the study here. So the joy of algebraic expression. If you can see here, various dance forms are here, and when we take it with the students, they enact these movements and they write the equations to represent what they have learned. Students can conjecture equations and acting them out. They are also deriving various patterns, considering different paths to come to the original position, and thus following the spatial arrangement. Student making generalizations on their findings. This is the best part. When the students start finding their generalization, the joy, the sense of doing something on their own is really amazing to see. And then developing some equations and converting them into dance form again is a amazing act. So dance with mathematics is very important, and it plays a special role in maths education as such, because most students lacks understanding of 3D space and find 3D geometry very difficult. Dance can offer an embodied understanding. Dance can give them confidence and make mathematics really, they can live with mathematics. It creates a learning by doing environment, and also gives ample opportunity to think critically. This abstract nature of algebra can be brought into the concrete sense with dance, and students can definitely get deep insight into mathematics as a subject. So these are the things I really want you to show a small piece. I hope it plays here. So thank you. So mathematics with dance actually will create love and motivation for learning this subject. It will create an enthusiasm, appreciation for the subject, and it will be a relationship for life. Thus, by nurturing creativity and critical thinking, actually this will give a learning experience to the students. Thank you so much. You can see here this presentation was created with the help of Professor Ramanujam. I really thank him a lot, and also thank to Norbert sir for giving me this opportunity to present my work here. This is just the beginning. We are starting to think about these things, and I hope with your inputs also I will go on improving it. Thank you so much.
Okay, thank you, Shanti, for your interesting presentation. And now we are inviting our next contributed talker, our colleague Atea, to share his slides with us and to start with his presentation. The title of your talk is The Role of Mathematical Induction in Behavior Analysis of the People.
Hi guys, I am so happy to present my presentation, which under the title, The Role of Mathematical Induction in Behavior Analysis of the People. Also, I would like to thank for the people who organized this scientific conference and give me a great opportunity to meet you. Okay, let's start with the abstract. In this project, we describe the idea of applying mathematical induction with some example of the current use in life and how the theoretical idea can be used to analyze cases of the socialite use of mathematical modules and how they can be transformed into teaching. In other words, it is context that can help us to make evident how mathematics can be used to legitimize and justify decisions that directly and significantly affected the social dynamics of some communities and their lives of their habitats. And emphasize on some information related. The historical case of the mathematical induction has been used in mathematics was way back in history in 370 BC. Plato and Pappus used induction, but there are no evidence that they used it. May have contained in the early example of implicit inductive proof. Some people think that even in Euclidean geometry use the induction when he provide that there are infinitely many primes without there is no evidence that he used it. But some writers think that he implied it without being stated directly. The Italian mathematician Francesco Marculo did a non-inductive proof concerning the sum of the first n natural numbers, even though Marculo did non-evidence proof of. There are people who think that Pascal got his inspiration for the induction principle from the Italian mathematicians. When the Pascal in the 16th century showed by induction that the sum of the first n natural number, this is fact in references 11. Levy and Grazio use mathematical induction. He called the method rising step by step without end, comparing to how we are used to use induction, where the first do the base case and then the induction step to show that it holds for n to n plus 1. Levy started with the induction step and then he showed for the base. As you can see, mathematicians in history have used mathematical induction and inductive reasons for long time, but there were no one who had named this method yet. According to the information which post in references 12, the first ones who started to name induction was the Englishman John Wells and the Swiss Jacob Bernoulli. Mathematical induction is a special way of proving things. At the beginning of the 20th century, research on behavior developed depended on the concept of stimulus response bonds. Skinner in 1938 pointed the way to the new formulation that transcended direct discrete events and contiguity with the invitation of operant behavior. For a long time, mathematical modeling of the social system and dynamicals was considered in the realm of science fiction, but predicting and at one influencing human behavior is well on its way to become reality. Induction of a powerful method show probability is true for all non-negative integers. Induction plays a central role in discrete mathematics and computer science, and in fact, it is used in defining a characteristic of discrete and opposite to continue mathematics. In section 1, in this section, we introduce the main idea which will be used during our work. Generally, mathematical induction is a special way of proving things. It has only 2 steps. Step 1, show it is true for the first one. Step 2, show that if anyone is true, then the next one is true, then all are true. Sometimes use mathematical induction as 3 steps. Now, suppose Y is any community has the elements x1, x2, x3, and xn elements. Let T any elements belong to another community, say W. The element T tries to examine the truth property for Y community, i.e. determine whether the elements for x1, x2, x3 until xn have the truth property. Now we start the procedures. First step, the element T examine x1 and find the result satisfied or unsatisfied. That does not mean the community Y satisfied or unsatisfied that property. For example, x1 has the truth property. Maybe x1 or x3 or xn has not that, and vice versa. Second step, that means we must go to the second step. Second step, assumption we have another community, say K, and suppose that Y equal K is true, That's mean K satisfies or unsatisfy that property. Indeed, the result of Y is still not sufficient to make the final decision about Y has or hasn't that property. Hence, to be more confident about the decision, we investigate Y equal K plus 1, which mean the community, the community Y equal to K with the extra element is also satisfied or unsatisfied. This case mentioned that property not restricted to community K. It is covering another element from another community. The type of the result concerning K plus 1 gives us the gradual decision Y has the same type of the result. Prospective application of this technique, some sector could be used this technique, education study the response of the students at the secondary school in Baghdad to challenge questions of mathematics, social studies, for instance, studies the response of the community to obey the regulation of safety from COVID-19. Studied the culture and comparative among the communities as a matter as doing kind of habitus between two communities. Media, especially the program which deal with the behavior of people, teaching of university, schools, and other political studies, for example, the situation of small region may be covering a large area. Actually, I find this technique, it is more advanced, and we can get the researcher a correct answer, because sometimes we can find the decision or idea or opinion of maybe, let's say, practice, but it's not cover all that community which we studied it. Finally, I lost some references during my work. I depended on it. I hope it is help the people who interest to study in the same way, and if have any other opinion. Thank you so much for all.
Thank you for your talk.
Okay, so hello everybody. I'm Dragana Martinovic from University of Windsor in Canada, and I will be chairing the rest of the today's session. The first speaker today is Volodymyr Mazurchuk from University of Uppsala, Sweden, and he'll be talking about representations of generalized Rook monoid algebra. Please go ahead.
Yeah, thank you very much. So we start 10 minutes early, right?
Yes. A little bit less than 10 minutes.
Okay, thank you very much. Thanks a lot for this opportunity to give a talk at this conference. My talk will be quite hardcore mathematics, and I'm going to talk about representations of generalized Rook monoid algebras. And I will start with describing the classical thing which we generalize to the case of the Rook monoid algebras, and this is a case of the representations of the symmetric group. So let n be a non-negative integer, and then we can consider the corresponding symmetric group of all permutations of n elements. So if we fix an algebraically closed field K, then we have the associated group algebra of Sn over K. So simple modules for this group algebra, they are indexed by partitions of n, and usually S lambda denotes the simple module called the Specht module corresponding to a partition lambda. So if the characteristic of the base field is 0, then the set of all Specht modules for all partitions forms a complete and irredundant list of simple modules for the symmetric group. However, if the characteristic of the base field is positive, then some Specht modules might be not simple. So the partition lambda is called P regular, so where P is a fixed prime number, the characteristic of the field, if it doesn't have P parts of the same positive lengths. And if the characteristic of the field is P and lambda is P regular, then the module S lambda is known to have simple top, denoted L lambda, and then such L lambda, now indexed by P regular partitions, form a complete and irredundant list of simple modules for the symmetric group over such a field. Important role in the representation theory of the symmetric group is played by the so-called Eutsys-Murphy elements. So here they are. They're very easy to define. So there are exactly n Eutsys-Murphy elements. The first one is always taken to be 0. And then the element xk, where k is between 2 and n, is just the sum of all transpositions 1k, 2k, and so on, k minus 1k. And the subalgebra of the group algebra of the symmetric group, generated by all Eutsys-Murphy elements, is called the Gelfand-Zeitlin subalgebra. So if we denote by z of ksn the center of ksn, so the original relevance of Eutsys-Murphy elements for the representation theory of the symmetric group is given by the following theorem by Eutsys, that the center of the group algebra of the symmetric group is generated by the symmetric polynomials in the Eutsys-Murphy elements. And then the next development, the next point of relevance of this algebra for the symmetric group is the following. So if we consider the flag of standard inclusions, S1 embedded in S2 and so on up to Sn in the natural way, then there is a theorem due to Okunkov and Vershik, which says that the Gelfand-Zeitlin subalgebra, so the subalgebra generated by Eutsys-Murphy elements, it coincides with this commutative subalgebra of the group algebra, which is generated by the centers of all components of this flag of inclusion. And the most important for us property of Eutsys-Murphy elements is the following. If we work over a field of positive characteristic P, then the eigenvalues of all Eutsys-Murphy elements on all simple modules for the group algebra, they all belong to the prime subfield Fp of our field K. So basically they are integers in the sense of positive characteristic. So now let's talk a little bit about induction and restriction. So as we already said, so Sn is a subgroup of Sn plus 1. So we have the natural induction functor. We can take an Sn module and induce it up to Sn plus 1. And similarly, we have the restriction functor. We can take Sn module and restrict it to Sn minus 1. So by convention, we define restriction from S0 to S minus 1 just to be the 0 functor. And now let us consider the direct sum of module categories over all symmetric group at the same time. Okay, and then we have the induction functor on this direct sum given by induction from each n to each n plus 1, and the restriction functor also on this direct sum given by restriction from each n to n minus 1. And the combinatorics of these functors on this very big category is given by the following branching rules. So over the complex numbers, if we take the Specht module S lambda and induce it to some module over Sn plus 1, so it decomposes it as a direct sum of Specht modules with multiplicity 1, where the index runs through the set of all partitions of n+1, which can be obtained from lambda by adding a so-called addable node. And similarly for restriction, if we restrict a Specht module to n-1, we get a direct sum of Specht modules for n-1 indexed by partitions for n-1, all with multiplicity 1. And these partitions are given by taking the original partition lambda and removing from it a removable node. Yep. Now, the next slide I will go very quickly. Basically, the slide says, if we take our important property of Eutsys-Murphy elements, that over field of characteristic 0, the eigenvalues of Eutsys-Murphy elements always belong to the integral prime subfield of this field. So then the point is you can cleverly collect these eigenvalues in junks so that you will get a decomposition of any module following these collections of eigenvalues for Eutsys-Murphy elements. And then using this decomposition of any module over the symmetric group according to eigenvalues of Eutsys-Murphy elements, we can split induction and restriction functors into direct summands. So here I am now going towards the main classical result. So given this collection of eigenvalues for Eutsys-Murphy elements, we denote by gamma plus minus I, just adding 1 to the i's component of this collection. And then we can define the subfunctor int I of the induction functor, starting from such a direct summand, inducing it up, and then taking the direct summand which corresponds to adding 1 at the i's component. And similarly, we can define restriction. We start from a direct summand indexed by some collection of eigenvalues. Then we restrict it, and we look at the component indexed by when we subtract 1 at the i's component of this collection of eigenvalues. So we started from all module categories over all symmetric groups. We had the restriction and induction, and we refined this picture to the same category, all modules over all symmetric groups, but now we have the i's component of the restriction given like that, and the i's component of the induction given like that. And now we can take the Grothendieck group of all this thing, and then we have some kind of vector space, so Z modules, we can induce scalars to complex numbers, for example, and then we will have a vector space and the collection of endomorphisms of this vector space. And then the classical result by Lascaux, Leclerc, and Thibon, and by Groinowski, asserts that on the level of Grothendieck group, the linear operators, induction I and restriction I, satisfy the defining relations of the affine Kac-Moody algebra as LP hat. So here P is the characteristic of the field. And moreover, you can identify, so this defines on this vector space, the Grothendieck group of F, the structure of a module over an affine Kac-Moody algebra, and you can explicitly identify this module. So this is the so-called basic representation of this affine Kac-Moody algebra. And this is what I plan to generalize, and I plan to generalize it to the setup of so-called generalized Rook monoids. So the Rook monoid is a monoid of n times n complex matrices with entries 0 and 1, such that each row and each column contains at most 1, 1. So we have seen almost this example in the talk of Mikhail Volkov today in the morning for n is equal to 2. So it was almost the Rook monoid with one matrix taken out. So an alternative name for this monoid is, it's also called the symmetric inverse semigroup. So what is a generalized Rook monoid? Let us fix a positive and non-negative integer r, and let psi be a primitive r's root of unity. So denoted by CR, the cyclic, multiplicative cyclic group generated by this element Xi. And then the generalized Rook monoid is defined simply as the Riesz product of this group CR with the Rook monoid Rn. And it basically means that whenever we have one, we can replace one in the Rook monoid by some power of Xi. So the example C2 Riesz R2 consists of one matrix of zero rank. It's a zero matrix, there is nothing to replace. But now we have 8 matrices of rank 1, because in matrix of rank 1, you have only 1, 1. And you can replace it by 1 or minus 1. And this one can be in 4 places. And we similarly will have 8 matrices of rank 2. Okay? And here is a little bit about simple modules over generalized Rook monoids. So the Green's relations in generalized Rook monoids are very easy to describe. In particular, Green's relation J, the two-sided ideals, they're simply given by the rank of the matrix. So two matrices are J equivalent if and only if they have the same rank. And the maximal subgroups in generalized Rook monoids are all isomorphic to the Riesz product of CR with the symmetric group indexed by some K, which is at most N. It is very well known that simple modules over such Riesz products are given by collections of partitions, lambda 1, lambda r. These are partitions of K1 up to Kr, such that K1 plus K2 plus and so on plus Kr adds up to K. So in particular, from this it follows that simple modules over the generalized Rook monoids are indexed by collections of partitions, such that these K1 and so on Kr add up to some K, which is at most N. So let's denote such module by L lambda. And the branching rules for the Rook monoid over C looks as follows. It's very similar to the branching rule for the symmetric group with one addition. So when we induce, we can get all possible multi-partitions which are given by adding one addable block, or we can stay in lambda. And similarly for restriction, when we restrict, we can remove a removable block, or we can leave lambda intact under the assumption that the sum of parts of lambda is strictly less than n. And this is important for us. Okay, so now I'm coming to the results which I plan to present. And first of all, it's the construction of Eutsys-Murphy elements. So let Q be the diagonal matrix which has Xi, this is our fixed root of unity, in position 1, 1, and other diagonal elements are 1. And P, let it denote the diagonal matrix which has 0 in position 1, 1, and all other diagonal elements are 1. For any subset A in 1 to n, let En be the diagonal matrix which has 0 at all diagonal position indexed by elements of A, and the rest is 1. And define the capital A as a sum of all these ABs, where B is a subset of A, and with coefficient -1 to the power cardinality of B. And then define one more diagonal matrix denoted in this way. So we place the else power Xi at position MM, and the minus else power Xi at the position JJ, and all other remaining diagonal elements are 1. So now the Eutsys-Murphy elements in this situation, they come in two groups. So the first group is the elements Xi defined in the following way. So X1 is Q minus P, and then Xi is just the conjugation of Xi minus 1 by the transposition I minus 1i. And then we have elements Yi, Y1 is 0, and then Yj is given by a horrible formula involving all the previous matrices. So it's much more complicated than the case of the symmetric group. And the claim is that these elements are exactly the Eutsys-Murphy elements for generalized Rook monoids. So here are now the results. All the results which I'm talking about from now on are joined with Shraddha Srivastava, who is a postdoc at Uppsala right now. So first of all, uses Murphy elements for generalized Rukmanoid algebra, they pairwise commute. And we can define the Gelfand-Zeitlin subalgebra of generalized Rukmanoid algebras as a subalgebra generated by uses Murphy elements. So, and if we consider the Gelfand model for this algebra, this is the direct sum of all simple modules with multiplicity 1, then we have an analog of, let's say, Acunco-Wierzyk result that the Gelfand model for generalized Rukmanoid algebras has an eigenbasis with respect to the Gelfand-Zeitlin subalgebra. Moreover, the action of the elements of the Gelfand-Zeitlin subalgebra distinguishes elements of this eigenbasis. And further property, which is very important, that if R is equal to 1, then the eigenvalues of all xi's and yi's on the corresponding eigenbasis here are actually integers. And also an analog of Yutz's theorem that in the case R is equal to 1, so just for the usual Rukmanoid, the center of the semigroup algebra of the Rukmanoid is generated by the symmetric polynomials in xi's and the symmetric polynomials in yi's. So now we can similarly define induction and restriction. Rukmanoids, now we consider Rukmanoids. Rukmanoids are embedded into each other. So if we assume that K has positive characteristic, we can consider the category of the direct sum of all module categories over all Rukmanoids in this flag. And similarly to the symmetric group, we can induce and restrict with respect to this flag. So we have endofunctors of induction and restriction. And because of the integrality of the eigenvalues of Yutz's Murphy elements, we can split induction and restriction into, we have the corresponding direct sums and sub I, where I is an element of the prime field in K. The problem is that in the branching rule, we have this additional components that lambda can stay the same. So we have to define two additional components in induction and restriction, is when you induce some module and then take the direct summand which corresponds to the same gamma. And similarly for restriction. So we have two additional components in the induction and restriction functors. And now we have to identify what they are. And for this, I need to discuss one more semigroup. This is the so-called bicyclic monoid. This is a semigroup generated by two elements whose product is 1, only in one direction. They do not commute. And this semigroup has the classical action on positive integers by partial transformations. We just can shift integers one step to the right. The element A does this, and B shifts it one step to the left. And if we linearize this action, we have a unique simple module over the semigroup algebra, which has infinite dimension. Let's denote it V sub n. I know that this semigroup has also a lot of finite dimensional simple modules, but this is a unique one which has infinite dimension. And here is the main result. So the theorem joined with Shraddha. Part A, on the level, this is very similar to the symmetric group. On the level of the Grothendieck group, the linear operators of the ice induction and the ice restriction satisfying the defining relations of the affine Kac-Moody algebra SLP hat. But now this is not the whole picture because we now have two additional operators, A and B. So part 2, on the level of Grothendieck group, the linear operators corresponding to A and B, they satisfy the defining relations for the bicyclic monoid, and they commute with the ice induction and the ice restriction. So now we no longer have a module just over the affine Kac-Moody algebra. We also have a part which comes from the bicyclic monoid. And we can identify explicitly this module. So as the module over the affine Kac-Moody algebra tensor, the bicyclic monoid, we get exactly the basic representation of the affine Kac-Moody algebra tensored with this unique infinite dimensional simple module over the bicyclic monoid. And so this is the result. So the reference for this result is our very recent preprint, which is called Eustace-Murphy Elements and Grothendieck Groups for Generalized Rook Monoids. Thank you very much.
Thank you very much, Dr. Muzarchuk. The next presenter is Dr. Boricic, Dean of the Faculty of Economics, University of Belgrade, Serbia, and he will be talking on mathematical aspects of simple social notions.
See now,
yes, we see your
document, and you can see that, for instance, by green marker, I marked the word complex. Do you see that?
Yes.
Yes. Thank you. Thank you. Look, it is great pleasure to take the part on this conference, and my congratulations for this well-organized conference. Unfortunately, we were not able to visit Niš today, but I hope that we will have this opportunity very soon. Look, I will close my camera and I will proceed with presentation in the same way as I make the lectures to give a lecture to my students. Look, I will talk about some subject regarding social choice theory. I will talk about part of this theory, about fragment of social choice theory, and my problem as I teach this part to my students, which are not mathematicians. Always I have problem how to present this some of very simple social notions in a complex mathematical context. So I believe that an alternative title of this talk could be on complex mathematical aspects of simple social notions. Look, and I will talk about some fragments of social choice theory. My talk will be divided into 3 parts: some introductory notes, some pure logical aspects of social choice theory, and on some aspects of mathematical analysis. In this introductory note, I will emphasize that one of the basic problems in teaching elements of social choice theory is the phenomenon of impossibility. From a logical or methodological point of view, we can divide formally all mathematical statements in 2 forms. One is the form of impossible, and the other one is the form of possible statement. We know that the first non-trivial impossibility in the history of science was the fact that square root of 2 is not rational number. And it is interesting that in the history of science, it was maybe the first known use of indirect argumentation, namely in the proof of this fact was used the reductio ad absurdum method. After that, from the ancient Greece, we have on 2000 years later, we discovered that the three famous problems of ancient Greek mathematicians were squaring the cycle, trisecting the angle, and doubling the cube. And it was the final result was that each of these problems is unsolvable, or that each of these hypotheses is impossible. So to my students, it is very difficult to understand the notion of impossibility. But in the social choice theory, the first important and simple example of impossibility was the so-called Condorcet paradox. Condorcet was a French sociologist and mathematician of 18th century. His example was can be presented in the following way. If we have a group of three individuals, A, B, and C, and connect with each of these individuals some preference relation better than from the point of view of A, better than from the viewpoint of B, and better than from the viewpoint of C. And if this relation is transitive for each individual, and if their preferences can be presented in the following way, that individual A said that X is better than Y and Y is better than Z, and individuals B and C say the similar, but in cyclic order. In this way, it is if the problem is what is the final preference relation belonging to this group, we will see that it is impossible. It is impossible to define any decision by this group. I will tell that this approach is strictly in social choice theory is called as ordinal approach. Another possibility is to give some cardinal approach, which is characteristic for utility theory, where the basic notion is the so-called utility function, and the context of cardinal social choice theory is easier to make analysis. So we see that in this approach we will have a problem how to define axioms of social choice theory, axioms which will not produce impossibilities. I will give here some elements of the traditional social choice theory. In order to explain that, I will just say that we can imagine that we have some ordered n-tuples of individual preferences, say R sub 1 to R sub n, and the problem how to generate, these are individual preferences, how to generate a social preference. This transformation from this path of from the individual to the social preference relation is usually called a social welfare function or social decision function, and so on. And you can see that some hypotheses regarding all these preference relations are purely in logical way defined as linearity and transitivity and so on. And you imagine, because these are very abstract notions, how difficult is for students which are not mathematicians to understand this. And this is not the main problem. The more complex problem is that Kenneth Arrow, I didn't say at the beginning of this talk that the basic result that we will analyze will be result obtained by Kenneth Arrow, which are Nobel Prize in Economics in 1972, and Amartya Sen, also Nobel Prize in Economics in 1998. And the main problem is that this axiomatic theory of social choice is based on some axioms called in the literature as Arrow axioms. The first of them is axiom of unrestricted domain, which says that the choice function can be applied to any profile of logically possible profiles of individual preferences, and axiom of independence of irrelevant alternatives also presents some conditions which are in fact the conditions belonging to higher order languages in formal logic. Look, just this part, if we roughly present it in logical language, we say for any profile R sub 1, R sub n. This is quantification over binary relations, and this is not first order language. This is not first order language, and it means that it is a very complex notion. And there are also two axioms belonging to Arrow's original theory. This is non-dictatorship axiom, stating that there is no person I, called dictator, having such power that for all profiles and each two alternatives, if I prefers X to Y, the society must prefer X to Y as well. And another important axiom from the original Eros theory is the so-called Pareto property, which also have some parts, this quantification over relations, quantification over all profiles. And the famous, which called the general possibility by obtained by Eros, was that there is no social welfare function satisfying those four axioms. I would translate this theorem to a pure logical context, and the translation will be that these four axioms are inconsistent. And I think that this is easier way, more approachable to students to present correctly some parts, some fragments of social choice theory. Another, I would say, easier theorem in this context of social choice theory was the Sen's impossibility theorem. Sen, who introduced a new axiom, liberalism axiom, which can be presented in this way. It is not important now, but Sen's impossibility theorem says that in this logical presentation that these three axioms are inconsistent. And I think that this is easier for my students to understand the Sen's impossibility theorem. And in this talk, I will say something about new axiom, which is defining the so-called Vitoire. Vitoire, unlike a dictator can impose a social preference, but Vitoire just can block any social preference, any social initiative, and in a descriptive way, traditional Vitoire condition can be formulated in this way. There is a person Y, person I, Vitoire, having such power that for all profiles and each two different alternatives X and Y, if Vitoire prefers X to Y, the society cannot prefer Y to X. And this is this short introduction. I would present in brief a method of simplification of these axioms. I would just mention some basic facts. We saw that the form of these axioms is one of these logical forms where it is important to say that this part for each profile P, this is the most difficult part of these statements, and we will substitute this form of axiom by this one on the basis that in general logic we know that there is an X, so that for each Y holds A, then for each Y there is X, so that A. This is generally logical theorem, and in this way, if we can move this universal quantification for each Y in front of this axiom, and then to move this for each Y because this is belongs to higher order language, and if we put this for each Y to meta theory, to meta language, we will obtain finally, instead of this form of axiom, we will obtain this form of axiom, and this finally will have the final result as follows. Here we have traditional Vitoire condition, where here we have this problematic higher order language, and for instance this Pareto rule traditional form, we have here this for all profiles higher order language axiom. If we accept their variations V and P, with supposing that these variations holds for all profiles P in meta language, knowing that V, this is deduction relation, that V follows from TV and that P follows from TP, and if we substitute these two axioms by these two axioms, then we obtain some from the social choice theory, we will obtain some fragment of social choice theory based on V and P, and we know that this sub-theory will be, if this sub-theory is inconsistent, then its extension, original social choice theory T, will be inconsistent also. So that we will obtain again a context which is good enough to prove or to give argumentations for inconsistency or for impossibility results. And in this way, and look, another step of simplification can be the following one, when we, from the first order language, we pass to propositional language. I would say almost propositional, because this language will be an extension of propositional language with one new binary relation P for social preference relation and P sub I for individual preference relation. So formally speaking, we obtain a very simple context, logical, for presenting some parts of social choice theory. And this, I believe that in this way, we preserved the spirit of formal logical treatment of descriptive social choice conditions. We reduced the complexity degree of conditions under consideration, and we enabled simplified argumentations for some social choice impossibilities. And finally, I will just tell you what of the known or unknown impossibilities, including vetoing, dictatorship, and Pareto rule. These are three axioms in new form, without this difficult quantification over relations and their negations. In this context, we are able to prove some knowns and some new results regarding impossibilities. We are able to, and this is a short proof of this note, that conditions for dictatorship and non-vetoer are inconsistent. Another lemma is impossibility of non-Paretian dictator, presenting the fact that conditions D and NP are inconsistent, and this is just a fine, a short, and I think approachable proof. And we have another new lemmas and theorems regarding these conditions. Here is in the literature known as the weak dictatorship condition, which is in context of this simplified approach, can be proved that vetoer and this weak dictatorship condition are logically equivalent. It is possible to show also a statement regarding the impossibility of Paretian non-vetoer, or that Pareto principle and non-vetoer condition are inconsistent. And that's all. Another part which is prepared by with me and with my co-author of another part of this paper is regarding mathematical aspects of vetoer, and this will be part of our paper which we prepare for this book. Okay, thank you.
Thank you very much, Dr. Boricic.
Can you hear me?
Yes, we can hear you, Marcel. Well, thank you to the organizers for beautiful images from Windsor, Ontario. Finally, we see some beauty of Canada. Thank you. So that's a good introduction to our Canadian speaker, Dr. Marcel Danesi from University of Toronto, and he will give us introduction into semiotics of mathematics.
Thank you. First of all, let me say I feel extremely privileged to be part of a group like this. I'm probably what you would call a closet mathematician. I love this stuff, but I don't do it professionally. And when I engage in this sort of thing, I guess I'm engaging in my own personal needs. I'm a linguist, a semiotician. And what I'm going to speak about today is how perhaps the theories of mathematics, mathematicians who work unconsciously on using signs and symbols, how semiotics can shed light on those signs and those symbols, and how they can be used to create systems and networks of meaning that go beyond the merely representational or annotative. So I'm going to divide it into 3 or 4 parts, and I will be quick. This might seem, I've had this before, especially at the Fields Institute where we are located, the Cognitive Science Center, whatever it's called. You get the reaction that, well, so what? I can still do mathematics. Well, I like to compare it to music theory. Musicians play, they're not thinking of the chords, what harmonic progressions are. But knowing them probably will make them better composers in the end, because you think, aha, I should move in this direction. Let me try it here or there. And this occurs in all areas of life, because semiotics studies what one of its founders, Charles Peirce, we'll discuss in a second, called semiosis. One of my students says, is that a disease? Well, I guess in a way, it's a disease of the mind because it's constantly generating meaning, interpretations, and then organizes these in terms of systems and codes, language, music, mathematics, and so on. So let's get to the background. Has semiotics ever contributed in any substantive way to understanding mathematics? No, it has not in any substantive way. Indirectly, yes. In fact, I would say that there were 3 major figures in this area, 2 of whom identified themselves as semioticians, and one probably was. The first one is Charles Peirce, American logician and mathematician, who really presented the first truly complete theory of signification, semiosis, how we organize our feelings and expression in terms of codes. And each code, language, has its signs, has its rules, the way of organizing, but at the same time, each one of these codes provides a perspective on reality, and it's the interconnection of all of them that is critical in semiotic theory, which I'll come to at the end. So Charles Peirce, did he deal with mathematics directly? Not directly, but he was a great logician, and therefore he discussed the various shades and colors of logic, not as rigid in an Aristotelian or deductive syllogistic sense, but in Cantorian way, and I'll get back to that in a minute. Second one, René Thom, T-H-O-M, whose theory of catastrophes was really a semiotic theory, and I had the pleasure of editing his crucial work in the Encyclopedic Dictionary of Mathematics, edited by the late Thomas A. Sebeok, in which I revised and I think it was in 2010. And rereading over his entry, I was able to see the connections that could be made from the mathematician to theories of representation. His term semiogenesis is crucial in this, meaning that once we've represented something, once we have an equation, I'll give a banal example, the Pythagorean theorem. Once we have that equation, we have a semiotic artifact. Once you remove it from its context and start connecting it to other areas of the world, it becomes a semiogenetic form. And so you will get everything from, the theory of triplets. It's been used in prime numbers, and of course, Fermat's last theorem, semiogenesis. And last but not least, of the third of the 3, how we say, founders of the semiotics of mathematics is the late Solomon Marcus, a Romanian whom I had the pleasure of working with for quite a number of years through Thomas Sibiak, who, if you recall, Dragana, he was one of the first people we invited over to the Fields Institute, who was among the first to see the relationship between creative language, figurative language, and cognition, and how the two not only lead us to understanding language, but also to understanding mathematics, where he was the one that claimed first that all of mathematics, not just some of it, all of it is metaphor, which leads me to the work of George Lakoff and Mark Johnson and Rafael Nunez, Rafael Nunez, both of whom came to our conferences at the Fields, in their 2000 book called Where Mathematics Comes From. And while not directly semiotic, and in fact, Rafael Nunez and I have had many arguments over not only espresso, but prosecco at the espresso. It is pure semiotics in my view. What is that book about? Because I figure that that book in 2000 laid the foundations for what can become developments within semiotics for studying mathematics. I'm doing it an injustice by summarizing it, but I'm going to try. The basic idea in their approach is that mathematical thinking, cognition, and including how mathematicians evolve their proofs, their notations, is based on image schemata. Now, what is that? Again, let me simplify. If you take a container in real life, you know that a container, you can put things into it and take things out of it. It can be full, empty, partially full, and so on. This image schema, this experience becomes an image schema. So when I speak about memories, for example, in English, I can say, oh, my mind is full of memories. What am I talking about? Well, I'm using the container to speak about memories because I cannot really talk about them directly. Someone said to me, "Boy, your head is empty." Well, thank you. That the container. The container is not only found in speaking about memory or the mind, but it's found throughout the human expressive system. So I'm full of love. Our love is now empty. There's nothing there anymore, and on and on and on. Well, what Lakoff and Nunez saw, that exactly happens in mathematics in the same way, but receives an expressive symbolism that is different. Arithmetic is the container, more or less. Relationships of well, subtraction will be taking things out of the container, addition putting them into it, and on and on and on. That's the basic approach in that marvelous, well, not marvelous, but because it was a very controversial book. I should say that since Dalia Fish is probably going to be here, we are in the process, together with Dragana, of putting together a handbook of cognitive mathematics, in which this theory of Lakoff and Johnson, of Lakoff and Nunez, figures prominently. Okay. By the way, in a sense, if you are a literary critic, you will see that poetry, in a very explicit way, uses image schemata. In other words, those figures that the poets use are nothing but image schemata. And that leads me to think of Einstein and other mathematicians, but Einstein in particular, who said, pure mathematics is the poetry of logical ideas. How true, and how much Lakoff and Johnson were able to bring this about. Okay, so what would a semiotic theory of mathematical cognition look like? What would it be like? It is actually a simple theory. And, you know, people say, well, simplicity, that means nothing. I remember I was a student of Marshall McLuhan's at the University of Toronto in 1965. And I remember one student saying to him, but this is too simple. So McLuhan turns to him and says, well, I got a lot of complex ideas. Which ones would you like to hear? Because reducing things to their bare bones is what really semiotics is all about. in representational theory. And I'm going to use Charles Peirce again. He said there are 3 levels, nothing new. Many religions, philosophies talk about body, mind, spirit, body, mind, context. Karl Popper in his brilliant work on science, the hermeneutics of science, called it World 1, World 2, World 3. But perhaps no one like Charles Peirce was able to give a generic, he was a master of words. And that's why he's also difficult to penetrate and needs interpreters, semioticians. 3 levels. The first one he called firstness. So what's that? Well, firstness is a reaction, a signifying semiotic reaction to things that we sense are in the world. In mathematics, it would probably be, well, I've been counting. Children do that, and they count and they distinguish things. I understand that many species, non-human, also can count. But it doesn't stop there at firstness. In human beings, we need a way of recording that counting, of reproducing it. In fact, the word reproduction here is crucial with Peirce. So I could put a tally, 1 notch on a wall. And if there's more than 1 and there's 2 of the same, then I put 2 notches, 2 tallies, and on and on. From this firstness, from this tallying, from this reproducing those intuitions and experiences, we get numerals. Numerals are not numbers. They are numerals. They represent numbers. At the firstness level, our first signs, in fact, historically in mathematics, are numerals. Experimentation with numerals, and they vary throughout the world. The idea, however, is the same, to reproduce in some way, and Peirce used the word iconicity for this, iconicity meaning a resembling system. It resembles the way we count spontaneously. It doesn't stop there. As we count and have numerals. These numerals then go to a secondness level. At this level, we start to compare them, relate them. What can we do with them? And it is at this level that numbers become arithmetic. Numerals become arithmetic. We look at them and see their relations. This is the level of relations, of showing how they exist one with the other. He called this the level of indexicality. Indexes are the ones that point to things and how they relate to each other. They don't reproduce them, they relate them one to each other. So at the secondness level, and as I said, I'm simplifying, the numerals, counting systems, which are a result of reproducing sensations and feelings and images and so on, become arithmetic. Then arithmetic at that secondness level becomes a code, a system, a way of using numbers, and then turning them around. They came from experience, from counting, measuring, what have you, and reflecting upon it. So it's a kind of cycle where arithmetic then helps counting, and counting other ways adds to developing arithmetic. It's a kind of, he called it a semiotic process. And then finally, if you keep on doing arithmetic, you end up representing arithmetical features and functions with other symbols and other forms, and you get algebra, which is, I think, what this is about. And algebra is really, and mathematicians call it nothing but arithmetic with letters. Well, it's a little bit more. It's the arithmetic of arithmetic. It is a generalization of it. It is at this level, which you call symbolic, so it's iconicity, indexicality, and symbolicity, not symbolism. At this level that the mind starts to interpret. He called that not interpretation, but interpretant, A-N-T, which is an ongoing interpretation, which is absolutely true. Once you have that thirdness level, then you have full-blown mathematics, the ability to lead then to numbers themselves. You get number theory, you can get linear algebra, you can get all kinds of things. You get meta-languages, which I heard just before. And in fact, Russell and Whitehead attempted to come to a meta language which was solid. Didn't work because the human mind may not be perfect, as Peirce himself said. And so our logical systems, as representational as they are, they're not rigid because of the interpretant, which is never complete and never foolproof. Now, I should add that this Peircean theory of semiotics is not the only one. There is a second view of mathematics and of science. Saussurian, Ferdinand de Saussure, who was a professor of linguistics, he coined the term linguistics. Before that, it was called philology, glottology, or something else in the mid-1800s in Geneva. And one of his insights that I think is relevant, which is not found in Peirce, but I still think it's relevant, is the idea of difference. What's difference? If I say to you night, then the only way to understand night is to oppose it to day. The difference that I get, which can be explained or not, allows me to understand both at the same time. Now, later on in Prague, the Czech Republic, they took this and called it, well, one of these two comes before the other, and therefore is cognitively more dominant. And most people will say it's probably day rather than night. This varies, and I'm simplifying. Why? Because, well, at night, most people sleep, unless, of course, you work at night, and then the opposition gets reversed. Okay, so you have one of the two poles in this opposition is unmarked. It's the one that's default. And the other one is marked. It's derived from it to finish the opposition. Well, if you look at mathematics, what came first? Addition or subtraction? Addition did. Mathematically, not intuitively, because we're always taking away things and adding to them. So you have positive numbers as the default. It took a long time to develop negative numbers. Why? Because that's the other side of the opposition that came later. Once you have it, the system is complete. Now, from these two oppositions, plus minus, then you get derivatives. Many pluses, multiplication, many minuses, division. And the square, the semiotic square, as it's called, is completed. So I, as a semiotician, do not fully put all my eggs into the Peircean basket. I see an awful lot in Saussurian semiotics and how it can be combined to explain many phenomena. The last part to this is called modeling systems theory. It's a kind of blend of both Peircean and Saussurian semiotics. And it really begins in Tartu in Estonia and goes back to a biologist, Jakob von Uexküll, who basically said, our mind is constantly modeling the world. And each species has its own innate capacity to model it in a certain way. And it's based on anatomy and physiology, evolution, and so on. In the case of the human being, he added history. So the historical process, our experiences from the past, and our biology interact to produce our models of the world. And these will always change. As the history changes, so does the modeling of the world. In a sense, mathematics is a modeling system. And let me digress very quickly and look at how modeling systems, once you have a new model, it changes everything. I'll go back to Galileo Galilei. Why not? I'm Italian, right? In his dialogues of two New World systems, I know the word and the name in Italian, I can't think of it in English. He comes up with an observation. He says, all the integers, when laid out, go on in infinity. Within that layout, there's my model, line. I see squares. So you get 4, 9, 16, and so on. If you look at it that way, he said, well, then there are more numbers integers than there are square numbers within it. In other words, square numbers are a subset of the overall set. He didn't put it in that way, but that's what he meant. And he left it at that until he said, but wait a minute, let me put them into a one-to-one correspondence. So he did, and you have that marvelous correspondence where you put all, on the top you have all the integers, and below it you put all the square numbers and match each one, and they never end. Conclusion, there are as many square numbers as there are integers. Ma pazzia, they said to Galileo, you're crazy, that is impossible. But I just showed you that it was. It wasn't until Georg Cantor took this up seriously and showed that these one-to-one correspondences occurs throughout the system of arithmetic, of numbers. And this one-to-one occurs because of infinity, one of the oldest notions that led to the greatest paradoxes of mathematics, starting with Zeno of, starts with an E, Elea, Zeno of Elea, Zenone, who showed that, things go on at an infinity, and you cannot explain infinity in very simple, finite terms. Well, this opened up a whole new vista of what mathematics, what set theories is, and so on. So much so that at one of our conferences at the Fields Institute, George Lakoff gave a brilliant talk of how Gödel, Kurt Gödel, used one of Cantor's diagrams, which is an icon. The diagonal one where he showed that the diagonal one. I don't know how to use visuals in this, Dragan. I'm sorry, you know me, technically poco bravo. Of how this idea became an image schema and allowed for Gödel to show that within that diagonal system, there will be a spot or a point where the system leads to, the theorem itself, or the set of theorems where there's a proposition that you cannot prove or disprove as such. Okay, so modeling led to a whole new way of looking at mathematics. Without that Galileo or Cantorian model of putting things in one-to-one, there would be no set theory. There would not be modern day mathematics. We'd still be doing Pythagorean theorems to this day. Incredible act of semiogenesis, going back to René Thom. Now, that means that all of discovery in mathematics is semiogenetic. And you know what? I think it is. What a claim, what an extraordinary claim. To make such a claim, I would have to show it. Well, that's one of the reasons why I started to delve into this. Because the more I do, the more I write about it, the more I look at it, the more it seems to hold some form of water. Pardon my metaphor. I'll give you one of my simple examples. I'm sorry, this is a little banal. I don't know how much time I have, but I'll be very quick. If you look at Alcuin's river crossing puzzle, I don't know if you recall it, a traveler comes to a riverbank with a goat, a wolf, and a head of cabbage, and there's a boat that can hold only two. How does he get him across safely? Because if he ever leaves the wolf and goat alone on either side, the wolf will lead the goat, and if he leaves the goat and cabbage, how does he get him across? Well, it's the first step. The first step. Once you make that first decision, then the rest of the system follows logically. So that firstness decision, what do I start with? Well, you start with, or if you start with the wolf, you're in trouble, because then the goat will eat the cabbage. If you start with the cabbage, you're in trouble, because the wolf will eat the goat. So you have only one choice, the goat. Once that happens and you take it across, and it's a back and forth movement, and then you're off and free and can carry them all across. Okay, seems like a simple, almost inane puzzle, but it is not, because it describes a situation, a pattern that comes up out of everyday life. Peirce called this a logica utens, a kind of practical logic that we understand. At that level, it remains that. If I start to represent it and use diagrams and schemas for it, I go into graph theory. Graph theory, which shows where the decision-making occurs. And from this, my claim is that you even develop flowcharts. The flowchart idea probably would not have occurred as a cognitive germ without this kind of thinking that can go right back to the late 700s and 800s in Alcuin. This is the secondness level, where you get graphs that are not just simple diagrams or reproductions. We're not at the iconic level anymore. We become indexical. And from this, you get graph theory. And graph theory is the basis of all kinds of things developed, for example, by Euler with his Königsberg bridges problem, and on and on and on. And that graph theory is the basis of computer programming. Not surprising that computer programs can be developed to model Alcuin's puzzle as an exercise in early simple computer science. I know that from the students that I have been teaching. Okay, I'm going to come to a conclusion of all of this. The question is, what is mathematics? And a brilliant little book by Hirsch, Davis and Hirsch, What is Mathematics? By the way, Ruben Hirsch, I was a member of our institute, or whatever we call it, and he just passed away, I think last year, if I'm not correct. He became a fervent collaborator, and I don't like to use the word belief, but in a certain sense, you have to believe that what you're doing is on the right path. And told me several times at our meetings and in correspondence that indeed this has something to tell mathematicians about how they do mathematics. And if you ask what is mathematics, then you'll have to ask what is music, what is language, because they're all connected to a basic system of signs, which are involved in a firstness, secondness, and thirdness dimensionality, which interconnects all of them together. You cannot separate any one of them. So music is mathematics. Even Pythagoras said that. Mathematics is music. Poetry is mathematics. Mathematics is poetry, and on and on and on. Because in the substratum, they show a semiotic pattern that is common to all of them. This is called interconnectedness theory in semiotics, and led the Tartu semioticians to the term of the semiosphere. The biosphere is where organisms adapt to the environment, and the semiosphere is where humans adapt to their science systems and to history. That means that mathematics is not just a genetic product. It's also a historical one. It includes what the Italians and what Giambattista Vico, my favorite philosopher, called the fantasia. And then when the fantasia works, it becomes the ingenuity, which is at the secondness level. And then the third level is memoria. It becomes memory, the way we do things. And then the cycle starts over and over and over again. So I conclude with a quote by Henri Poincaré, who said, "Mathematics is the art of giving the same name to different things." How true. Thank you very much for listening to me.
Thank you very much, Dr. Danesi. And please stay with us because we want to talk to you after Dr. Šikić finishes his talk. So he will be talking now about, let me check, Gödel's incompleteness theorem and human-machine non-equivalence. Dr. Šikić.
Yes, thank you very much. I will try to share the screen. Oh, somebody. Excellent. Well, my talk is not about application of logic in social sciences, but more about application of logic in philosophy, or more specifically, application of Gödel's incompleteness theorem to the mind-body problem. So how can I? Oh, thank you. So the problem of qualia is the hardest part of the mind-body problem, and it is often summed up in the question how matter becomes mind. And of course, we have a dualist answer and a materialist answer. Dualist answer is that it never does. And materialist answer is that there is only matter, and mind is just a product of matter and, of course, energy and all other physical stuff as everything else. But there is a specific argument by some dualists like Lucas and Penrose. They think that incompleteness theorem, Gödel's incompleteness theorem, especially the first one, proves that the mind cannot be reduced to any material mechanism, which means that Gödel incompleteness theorem implies human-machine non-equivalence in the following sense. So there is machine, or there is no machine which could capture all our mathematical intuitions. That's what they think the Gödel's incompleteness theorem proves, and hence we are not just mathematical, we are not just machines, because there is something beyond that. Well, I would like to show that this argument is not correct. It seems that somebody else is changing these slides, and thank him or her very much. So to understand what Gödel's theorem is all about, think about the following machine. You have a machine who in discrete moments, discrete periods of time, prints finite sequences of symbols, not prints and double, which is stroke P and B, and the meaning of these symbols are stroke for not, P for prints, and D for double. And some of these sequences are meaningful sentences. So some of them are completely without any meaning, but some of them are meaningful. So those of the form Px, where x does not start with D, is meaningful, and it means M prints X. So Px just means M prints X, and no stroke Px means M does not print X. And if what's after P start with D, like in P dy, it means M prints YY, which means double Y. And non-P dy or stroke P dy means M does not print YY. So it's a very simple machine which prints finite sequences of 3 symbols, and some of these finite sequences are sentences with meaning. So they are true or false, and only these sequences are true or false, all other are meaningless, of course. I would like to go further. So, because we have, because our machine prints sentences which could be true or false, we can define what does it mean that the machine is correct. Well, our machine is correct if it prints only true sentences. Well, it means that it could print non-sentences, but if it prints a sentence, then this should be, and this must be, a true sentence. This is a correct machine. A machine is complete if it prints all true sentences. That's all true sentences, I mean. So what we want from our machines is to be correct and complete, which means that it prints only true sentences and all true sentences. Unfortunately, we can very easily prove that there is no such machine, and the proof is so simple that it can be put on the rest of this slide. So if you think of the sequence non-PD, non-PD, it means, by our definition, that M machine does not print non-PD, non-PD, because non-P means doesn't print, and double non-PD means non-PD, non-PD. So we have this sentence with a very simple meaning, and if we start with a very simple fact that M either prints this sentence non-PD, non-PD or not, then we have just two cases. If M prints non-PD, non-PD, then it prints a false sentence because non-PD, non-PD means that this is not printable sentence. So in this case, our machine is not correct. But if machine M does not print this non-PD, non-PD sentence, then it does not print a true sentence because non-PD, non-PD says that this sentence is not printable. And in this case, hence, in this case, M is not complete. So here is our proof that M is not correct or is not complete. It cannot be both. And furthermore, so what is connection with our mathematical theories? Well, the connection is quite simple. A formalized mathematical theory with explicitly defined language, axioms, and deduction rules is a machine. And we may apply our simple theorem to this machine. There is one problem. The mathematical machines are not machines that produce sentences which assert something about itself, about the machine, because our machine is just such a machine. Our machine is telling something about itself. So in our mathematical theories, if we want to talk about our mathematical theory, we have to go to the meta theory of this mathematical theory. But then Gödel solved this problem because he proved that a mathematical theory which includes an appropriate amount of arithmetic may represent its own meta theory. And this is really the hardest part of Gödel's proof, because as we've seen, this existence of sentence which prove that our machines are never complete and correct is quite simple. Now, as a result, we have the following theorem, which is just Gödel's first theorem. If a formalized mathematical theory includes an appropriate amount of arithmetic, it is either incorrect or incomplete, which means if it is correct, then it is incomplete. And even more, we can explicitly define Gödel's sentence corresponding to before mentioned non-PD, non-PD, which is true but not probable in the theory. And I would like next slide. So now the dualist argument, the Penrose and Lucas argument, is any attempt to mechanize our mathematical intuition is doomed to fail because the very fact of mechanization yields new intuitive knowledge, which is Gödel's sentence, and this one is not captured by the mechanization. But what's wrong with this argument? The problem is that you have to know quite a lot about the specific mechanization, including meta-theoretic self-representation, to conclude that its corresponding Gödel sentence is true. In the specific case that Gödel analyzed, we know that that it is possible. But in general, it's quite possible that machine which is equivalent to our mathematical intuition actually exists, but we don't understand it quite enough to understand that the Gödel sentence is true. For example, we should be such machines. Next slide, please. So we can conclude that dualists like Lucas and Penrose confused the incorrect argument. There is no machine which could capture all our mathematical intuitions with the correct one, and which is there is no machine which would capture all our mathematical intuitions and which we could understand well enough to see that its Gödel sentence is true. So the second one is the real true sentence and the first one is not. So we may conclude, as far as Gödel incompleteness theorem is concerned, we could well be machines. There is no problem as far as Gödel incompleteness is concerned with this. But if we are, then we are definitely not capable of the complete knowledge of the machines. Here we are not capable of the complete knowledge of ourselves. So this is my main argument. And if you want to go into details, you can look at my paper on man-machine non-equivalence and Gödel incompleteness theorem, which is published in Grazer's Mathematisches Berichte and could be seen on my web page or on my profile on ResearchGate. So that's in very short terms my presentation about Gödel incompleteness theorem and the problem of mechanization of ourselves. Thank you very much.
Thank you very much, Dr. Šikić. I'm asking all participants, all attendees, to think about questions that they would like to ask the presenters. And while you are doing so, because we are going now into the part where we have a discussion, I will first invite Dr. Danesi to tell us a little bit about his Springer book series, in which we hope to publish a book that will come out of this conference.
Yes, I noticed that Dalia's not here. Is that true?
I don't think so.
It's too early in the morning. Anyhow, yes, about, it must be 5-6 years ago, at one of the meetings, first of all, it goes back to the foundation of an institute or a center at the Fields Institute for Research in Mathematics. We gave our first conference way back, I think it was 2011, and Dragana was at it. And it went so well, people became so interested in each other's ideas, which is what semiotics tries to generate, a kind of interdisciplinarity, that we founded this center. I forget the name of the director, the geometer. Would you remember his name, Dragan? I've had a blank.
Oh, you mean the field?
Sorry? No, before him. Before Ian, but it doesn't matter. Anyhow, so he invited me and said, look, this sounds very interesting. Could we not have a center within it? And I said, yes, let's have it. But of course, when we're in it, if you have a center and you just meet every once in a while, it doesn't have any lasting effect or any significant effect unless there are some publications of research or ideas going forward. And hence the idea of this series with Springer. It was given to me, the idea, by one of the editors there, Elizabeth Lowe, and then Dalia Fish, who became the editor of our series. He's a very strong promoter of it. And the idea of this series is not to do mathematics. Plenty of series there. Springer has a lot of them. But to look at what happens in mathematicians' minds as they do mathematics, but not only the mind, but in the cultural environment in which that mind existed historically, socially, and on and on. And that was the idea of the series. So we've already published quite a number of books in that series. One of them, I think the last one you have to help me here, Dragan, is what, on math education in the information age, I think, or
informatics. Marcel, I don't know if you noticed that among us is Jacek Woźny. I don't know if you see him.
Is that the one smiling over there?
Yeah,
okay, great. He's one of our authors. Now, going back to our last volume, not to promote it, but why not? That it shows exactly what this series is about. These are a bunch of papers that look at the information age, technology, the internet, crowdsourcing, and how this reflects mathematics as it's being practiced today, and how mathematics itself, through its use in computer programming and artificial intelligence, is driving the age, hence that interconnectedness. That's what the series is about. It also deals with some mathematical issue. Dr. Woźny's paper is about logic and computer programming, and we also have that Yair Neumann's wonderful book on, and that young woman from from Japan. I always forget these names. I think it's she's got another book coming out in the series. She was also part of it.
Kumiko.
Yes, Kumiko, right.
And universals of language.
Yes, exactly. So that's the idea. It is really, we don't call it semiotics. And I found out why we don't call it semiotics, either in the center or in the series, because it, some people will say, it's humanities, it's meaningless, and so on. We do say cognitive science. It has a different resonance to it. But let me assure you that it is semiotics, theories of representations behind it. For me, it's a dream come true. It'll be the last thing that I do. I'm retiring, as you know, in June from the anthropology department after 47 years of teaching. And it's one of the, it's going to be more than a hobby. So I intend this to go on, and I encourage people here to submit not only their contributions to this particular volume, which is being edited by Melanija and Dragana, but also to the series.
Norbert and
yeah, just send it to me. My yeah, absolutely, and or to Dalia or to Dragana, and the proposal. Then we take it from there. I think it's an exciting work. It is finally my late mentor, Thomas Sibiak, who died in 2001, would be absolutely thrilled by this initiative, because he always saw semiotics as being appropriated by those in literature or culture studies for their own ideological reasons rather than for scientific reasons. And therefore, I'm absolutely proud. So yes, we're on.
Thank you very much, Marcel. So he is inviting everybody to, if you have some good ideas of individual books or co-edited books, apart from the one coming from this conference, please go ahead and contact him. Thank you very much, Marcel.
Thank you.
So we are now going to go into discussion. Do we have any questions or comments from the audience? It could be speakers, it could be attendees. Please raise your hand. And I think you will be unmuted, or we can unmute, I don't know, because we don't have a chat right now.
Yeah, everyone is unmuted, and from tomorrow chat will be also available. There is a reason why we decided to control process of muting or unmuting and sending messages. It was because the first part of our program today, it was because of opening session when we have ambassadors as a guest. That was the reason why we have done this. But from tomorrow, everything will be in the usual way. So now everyone is unmuted. It's up to you to decide when you are going to speak or not. And thank you very much to all of us, of course. To all today's, I want to thank you to all our today's speakers.
Thank you.
Yes,
I enjoy it. As for me, I enjoy. I can say that I enjoy every.
Thank you.
Do you want to ask a question?
I would, if I may.
Yes, please.
I'm waiting my turn. Well, of course, I will repeat it again, but very quickly. Thank you to the organizers. It's a great conference. It doesn't happen very often that we have two ambassadors at the opening. That was rather a surprise to me. Thank you, Professor Danesi, for accepting my book into your wonderful Mathematics in Mind series. And thank you to the Springer, of course, for publishing it. My quick question to Professor Danesi and to all esteemed scholars who gathered here is, why is language so easy to acquire and mathematics is not so easy, not for everyone?
Thank you so much for that question. If I may just say something. So your assumption is that language is easy to learn or easier than mathematics.
It seems so, yes.
There are many people who think that mathematics is language and that it should be learned as language.
True, yes, but
who would like to answer?
We do all speak some language, have our native language, and not all of us do speak mathematics. None of my students, for example, linguistics students, whenever there is anything mathematical, they stop thinking and say silly things in their answers. Whenever they suspect there might be something mathematical.
Marcel, would you like to answer?
Yeah, the idea that simple exposure to language, we acquire the categories, and there is a process up to puberty where lateralization occurs of the language. This is absolutely true, but that can be interfered in as well. Now, you remove the context, you remove the input of linguistic materials, and the brain will not organize it. Now, the question would be the following. What if we provided a mathematically rich input within that environment? And I've read a few studies, not many. If we do, but mathematics, I don't mean, algebra or anything, but notions that allow the mind to understand what it is thinking and feeling, then there is evidence that mathematics is easier to acquire. One of the people that worked with us at the fields, his name was James Alexander. He called these three areas: pre-math, math, and then mathematics, the three levels. Well, at the level of pre-math is also the level of pre-language, pre-verbal language. It depends on the input, how rich it is, what is provided, and so on. We have a plastic brain, as Vygotsky, the Russian psychologist, said in the 1930s, also semiotician. And if, however, that plasticity is not worked on by the age of puberty, then certain skills, especially psychomotor ones, mechanical ones, may diminish or be more difficult to acquire. I mean, I'm a teacher. I want people to acquire throughout their lives. So having said that, I don't know of anything that you see, it was Noam Chomsky who came up with this idea that language, just exposure to language, you pick it up and so on. But his model was a syntactic one. It's based on a set of recursive rules, which is mathematical, which is not necessarily so. If you look at Lakoff and Johnson, and you look at Vygotsky, children think figuratively. They think metaphorically, poetically, said Vygotsky, where they make analogies all the time. Now, those analogies are done within language and linguistic concepts or verbal concepts. If that analogical mechanisms, which are in us, are shifted over to mathematical ideas and so on, then it could be, I don't know, that the two systems will develop in tandem. Having said that, there's always individual capacities and individual talents. And I have to tell you that when I see logical things like in your book, I say, what the heck is he talking about? When you go into it and follow it closely and you interpret it, then you understand it, which means that even someone who's not a mathematician or a logician has in herself, himself, the ability to decipher this because it's in the substratum of semiosis.
Thank you very much.
Welcome.
Do we have another question or another response? Or comment?
I would like to, hello?
Yes, Shanti, please go ahead.
So I would like to comment that I really enjoyed this mathematical disposition. First of all, my topic or the thing what I had taken, mathematics and its integration into dance, was I was thinking it was very low level. It was not pitched at very high level as such. But when I heard especially all all of you, I could relate to it, and I'm also enjoying this mathematical discourse, I would say that, and it's really truly enriching. So thank you so much for giving me this opportunity. I would definitely read more and think about it more, and especially I would like to work on the area of how mathematization process takes place. Right now in India, we have a new education policy which talks about mathematization of students' thoughts. And I was thinking this would be a very good platform to work with. So thank you so much. I really enjoyed this discourse. Thank you.
Thank you, Shanti. Actually, what Dr. Danesi was talking about, semiotics, also covers gestures.
Yes.
And facial expressions,
Yep.
even. So
Yes.
it fits nicely into drama, dance, and so on.
Yes.
Yeah,
So that's what I propose. Yes, sorry.
Yeah, mathematics and the arts actually is a subdiscipline. It's that person in California whose name at Pomona College, she runs a series in that area, and I have a series as well with Brill Academic Publishers that deals with mathematics and the arts and the humanities, because there's so much in common. The separation was, I think, an artificial one. We're coming to bringing it back together, and it's wonderful. And I miss your thing on dance, but I will read about it.
Okay, sure. Thank you.
Thank you.
Some comments. I think we had a very nice conference today. We attended very wonderful talks, and I would like to congratulate everyone for this distinguished day we passed together. Thank you.
Yes, thank you very much. Tomorrow we have also very engaging day, and day after tomorrow. So please come again. And any other question, comment? No? So what do you think, Melanija? Should we close today's session?
Yes, we can, but before that, we want to ask you something. We want to ask you to show yourself. We want to make a picture.
Okay.
Yes, I forgot about that part. Thank you, Melanija.
Yeah.
And I also
because we plan to make photos and to put them day by day on our web, on our conference web.
Daily
So,
photos. And I also forgot to mention, but it is on our website, that Springer is giving a discount to all attendees of the conference. So please visit our link. And if you have something, a book, your favorite book or something, you can get a discount from Springer.
so once again, please show yourself.
Use your camera.
Yeah. Start the video. Start the video. This is suggestion for those guys who help us to everything to go best possible way due to technical kind of things.
You can hear the sound of people dressing up now.
Yes, maybe they can show themselves. You want to show, you want to see the guys who are responsible. Okay, can you?
Excellent.
Thank you.
Hello.
Technical support part of Milan education. Okay, let's go. Let's make a picture. But there, yeah, of course, yeah, of course. We can. Okay, thank you very much. And Professor Hounkonnou, are we going to close?
Okay, so I would like to thank again all speakers for this wonderful day we spent together, and I hope tomorrow will be also fruitful. Thank you very much, and see you tomorrow.
See you tomorrow.
Thank you. Goodbye. See you, everybody.
See you.
Okay. Great day.
Prehistory, Antique Nisus, the Crusades, the Ottoman occupation, World War I and World War II. Experience the history of the entire Europe in one city.